Hey, Philip. Good morning. Can you hear us over there?
Yeah, good morning. Can you hear me?
Yeah, I can hear you very well. Thanks so much.
Perfect.
And one more thing, Philip, why don't you go ahead and share your screen just to give it a test before the event?
Sounds good. Okay, sorry, I think I had permission, but yeah, let's see. Um, okay, now that you stopped sharing, is my screen visible?
Yes, we can see it. That's
Okay,
great. Thank you so much. Okay, I think
perfect.
we can turn back to my screen. Morning, everyone. Can you hear me well with this mic as well? Okay, sounds good. Good morning one more time. So my name is Orhan. For those who were not there on Tuesday with the UXarray talk, I am a software engineer at NCAR CISL. I have been working at NCAR since 2019, and I have been leading the GeoGet team, geoscience community analysis team since 2020, I think June. And we are developing a tool, software tool, Python software tool, which is called UXarray, as I think majority of you can remember from last Tuesday. The efforts behind UXarray is Project Rygene and Project Seeds from DOE. I am the software engineering lead of the Project Rygene effort at NSF. And today I'd like to first introduce Rachel to you. So she was not there in the talk, but Rachel is our intern this year. And maybe a further background information. Philip was our intern 2 years ago as well. And he is now working full time with us. And he is working full time on Project Rygene. And he has a lot of great implementations that showed up in the released UXarray functionality. Philip will be with us virtually, but Rachel will be with me in person. And Rachel is off to a great start with Rygene internship this summer as well. We are working with Rachel on performance and scalability things of the project Rygene and UXarray. Rachel, would you like to maybe introduce yourself?
Good morning, everyone. I'm Rachel Tam. I'm currently a SciParks intern at NCAR, and as Orhan said, I will be working on UXarray and mainly working on scalability and improving, probably applying more Dask functions into incorporating Dask functions into UXarray and making it faster. And as we'll discuss more detail in a bit, yeah.
Thank you so much, Rachel. Before we start with the tutorial today, so it's gonna be a 90 minutes tutorial. We can go as slow as needed and wished. So if you have anything as a question or you would like to do something with us interactively, please don't hesitate. Just interrupt at any time, except the first 3 lines of code with UXarray to plot something. I'd like to uninterruptedly show that to you just to get a start. Then again, we can interrupt at any time. We can go back to anything throughout the tutorial, and we can look into things all together. So we would like to make this as interactive as teaching as possible. So I think 90 minutes should be more than enough for a lot of things we would like to show here. So after that, Philip, would you like to say anything, or are we good to go?
I think we're good to go. I mean, you already introduced me, so we're good.
Yeah. Okay, thanks so much. Okay, let's get started. I'd like to give you some background information and some initial notes about what today's tutorial is going to look like. So the tutorial, consists of a number of different natured materials today. One is the publicly available Project PITIA cookbook. That is what we put together to showcase the visualization functionality of UXarray. I'd like to show that to you all because it's really useful, not only during this tutorial, but also you can always use that as a self-learning resource about not only UXarray actually. I'd like to really show you what Project PITIA is about. So let me, this QR code is bringing you to this link first of all. And let me emphasize one more thing. All of these Project PITIA cookbooks, not only this unstructured grids visualization, is accessible via Binder, which means you can always give those notebooks a try on the fly. So you don't have to spin up any local environments for them. If you click on the Launch Binder buttons that are located in this spot in each of those cookbooks, you can right away start writing code on those notebooks for yourself. I think it's a very good resource for anyone who wouldn't like to set up any local Conda environment, but give a quick look into any Python code on the fly. So I'd like to show how it is working to you from UXarray's perspective. This is the UXarray cookbook. If you are here, you can click on this launch binder and it will spin up a binder instance for you. Then you can real time play with the code and write your own visualization things. Just play with maybe arguments to fine tune any of the plottings, and you can give them a try yourself. Uh, for ours, we will be going over the cookbook material, not executing them in the real time, but we are going to execute the notebooks we have in the HPC clusters of NCAR. I will be showing them to you as well. But before then, again, so Binder Hub is set up and spun up already. So it is good for me. And if you have spun up Binder for yourself, it is like this. Click on this directory, then it opens you a lot of these folders here. If you would like to, for example, run any visualization functions or notebooks, they are here. So if you would like to see plotting API or grid topology or whatsoever, let's say polygons, it's here. And it's real-time executable. And again, I will not spend time on this because I will be going over those rendered HTML notebooks today from the cookbook. But if anyone in the room would like to ask us any maybe adjustment of the arguments in any of those plottings, we can also do that. Turning back to Project PITIA, I think I'd like to really introduce this Project PITIA because not only for MPAS or unstructured grids purposes, if you are someone who would like to learn Python resources more, maybe if you are someone who is transitioning from NCL or something else into scientific Python ecosystem, Project PITIA is for you actually. So Project PITIA has a lot of resources like Python foundations that you can learn about the foundational skills and packages of Python. And you can also see a lot of application cookbooks from radar to unstructured grids. a lot of things here. I am not going to go into details of them for sure, because we are going to focus on MPAS applications of UXarray today. But again, if you would like to learn Python on your own, like self-paced, these PTIA cookbooks will be a great resource for anyone, just so you know. And our unstructured grids cookbook is located here, almost all the way down in the cookbooks list. This is the cookbooks of Project PTIA. If you go down all the way, and then it's here. Turning back, this is just one type of the materials we will be using today, Project PTIA cookbook for unstructured grids and UXarray. Another type of material is going to be live notebook sessions that we have in the HPC clusters of NCAR or Glade storage space of NCAR. I think not all of the people here have access to HPC clusters of NCAR. So how many people don't have access to NCAR's HPC clusters? Okay, so for you, we will be still providing these locations to the Glade storage space. I know NCAR can give permission to people from university and like collaborator institutions and things like that. So if you would like to give them a try, please reach out to NCAR source, and I think they can point you out to how to have access to NCAR HPC clusters. Because you won't have access right now, I think we would like to show them to you on the fly, and then we can again interrupt the executions and play with anything for your convenience. Go ahead, please.
Hi, good morning. This sounds really attractive, but I can tell you from where I work, I won't be able to gain access to NCAR's clusters. Does that mean I will not be able to access UXarray at this time?
No, definitely you can have access to UXarray. The only thing you cannot have access right now, at least during the tutorial, is some of the notebooks we put together, especially for MPAS Focus for this workshop. I think 3 of them are existing, and what we are planning to do is afterwards, maybe give us some, maybe 3-4 days, we will send them over to you, maybe with the help of Wei, so that you can have access to them as well. The only thing you cannot directly have access is maybe the Glade stored data sets. We can find some ways, I think, for them as well.
I think my colleagues have some MPAS data I could play with, but
That'd be great.
I
Yeah.
just wanted to make sure before I sit here that I would be able to do something with this. Thank
Yeah,
you.
definitely. UXarray itself, maybe that's a very good clarification question. UXarray itself is publicly released for several months now. So if you would like to go ahead, install UXarray yourself, it's available on Python package management systems like Conda and PyPy. So you can always do that. But only part of the notebook, Jupyter notebook materials that we put together, especially for this workshop, part of them are not directly available to those people who don't have access to NCAR HPC clusters. Is that clarifying the things? Okay, great, thank you. Yeah, this is that part, but again, we are still providing this location for those people who have immediate access and for those people who might have access after the event. And we will be sending over these notebooks to all of the participants after the event, maybe 2-3 days. One last thing is the publicly available UXarray documentation. We believe we have a very strong web page with a lot of well-documented structure like usage examples, notebooks, user guides, and everything else. So I'd like to show some of them to you before we get started. If you run this scan this QR code, you will be going to a web page like this. This is the immediate web page of UXarray. Oops. uxarray.redux.io, and this is the homepage. So if you are just getting started with UXarray, there is a bunch of useful documentation here. If you want to know about conventions of different unstructured grids, for example, the UGrid convention, then the terminology we are using here, because especially regarding the unstructured grids, there is several conventions and several different models available out there. And because of that, we have put together a very comprehensive user guide to bring a lot of people into the similar pages, even if not the same page. So conventions is here and supported grid formats by UXarray and core guides about a lot of UXarray implementation here. Some of the essential functionality and capabilities UXarray has as of today, like plotting, subsetting, remapping, tree structures UXarray provides as of today, and compatibility with other visualization and data analysis packages in the scientific Python ecosystem and things like that. And also API reference for those people who would consider further looking into the code of UXarray or maybe contributing to the code. So that was kind of an introduction of the material we will be using today. Turning back to the, by the way, we seem to have some questions online. First is from Abraham. I believe that the running on your own machine section should work on any system, right? Yeah, that's right, because UXarray is platform independent. If you are checking the Zoom questions, the question is about something like this. This is the cookbook, and I was telling you, you can always spin up your own binder instance from here. Also, each cookbook has their own README here about how you can get started using these cookbooks. This is the information about running on Binder. This is the information about running on your own machine. If you would like to get the cookbook running on your local laptop, you can also follow these instructions here. And the question was about if it could be done on any platforms. It is, because UXarray is platform independent as it is written in pure Python. So yeah, you can follow these on any platform like Windows, Mac OS, or Linux platforms. The second okay, yeah, definitely. Was that the only question? So okay, is UXarray only designed for MPAS outputs? Definitely not. And we would like to emphasize that very strongly. And some parts of the tutorial today is going to be emphasizing that in detail. Since this is an MPAS workshop, sure, today's focus is going to be MPAS datasets, but UXarray, especially emphasizing this, is supporting a lot of different models and grid formats such as MPAS, CAM spectral elements, E3SM, ICON and GOS soon. So we are representing all of those grid formats in a unified UGrid-like convention. And because of that, we believe there is a lot of strength with UXarray, like implementing, data analyzing, and visualizing all of those different grid formats in the same single interface is just one of them. So we would like to emphasize them more. But again, today's focus is going to be MPAS. Turning back to tutorial, and I wouldn't like to bore with a lot of introductory information here. So 3 different types of materials: 1 cookbook, notebooks, 2 NCAR HPC cluster notebooks, and 3 publicly available documentation. We will be switching from one to other throughout the event, but again, stop us anytime if you want some clarifications or have some questions. This is that. And for today's purposes, we will be using MPAS global datasets and also one regionally refined MPAS dataset that was provided to us by the organizers. And this is going to be showcasing UXarray's capabilities on regionally refined data sets as well. For NCAR people, UXarray is available on MPL environments of NCAR. So if you would like to use UXarray through NCAR MPL environments, it's up there. The latest version, MPL 2024A, is having UXarray natively. So that's just an information for NCAR HPC users. So I think we can get started now. If we don't have any questions or any concerns from the room or from Zoom. Zoom is good. Go ahead, please. Could you please maybe use mic, and if someone can help, thanks so much.
The directory you showed us on campaign, Glade campaign, is not readable by others or executable. I can't look at it.
Okay, that's a good point, and yeah, we can fix this afterwards. Okay. Thank you so much for this. Any more questions? And again, regarding the NCAR HPC cluster stored datasets and notebooks, I think the best way for everyone else's convenience is us sharing them through maybe email or something else, so that everyone can have access to them. Okay, if not, I think we can get started with the first part of the tutorial, which is we would really like to show you in just 3 lines of codes, you can get a global data or maybe a regionally refined data. I'm going to be using the global one in this one, plotted with UXarray. So for that one, I will be using NCAR's Glade stored notebooks. So give me just a few seconds. It should be here, not here, there. So this is the Casper compute nodes for myself, and I'd like to open this one here. And we have a very lightweight environment if you would like to set up your Conda environment from an environment file. It only has UXarray. This is an optional thing for color maps, CM Ocean, which provides you a lot of great color maps for ocean data analysis and visualization purposes. And Jupyter Lab is for having the Jupyter related benefits, but the only actual dependency here is the UXarray itself. So this is the plot from scratch. When I say 3 lines of code, please don't count these because I need these for data access. So the base path is one Glade folder we have, and this data set is a 30-kilometer resolution diamond data we got from one of our M-Cubed collaborators, Falco Jude, and thank you so much to Falco for this one. In almost any UXarray executions, you would need a grid definition file and a dataset file. If the data set is small enough, sometimes those models would be embedding the grid information into the dataset file, but many times, since you are going to have big data sets in unstructured grids, you would have the grid file definition in a different separate file. Because of that, we are having a pointer to a grid file and a data file. And what I'd like to do here is, what should be the first step in Python? Import UXarray as UX. Then while it is importing, the next step should be opening this dataset file as a dataset. UXDS is ux.open dataset. And I should first give the grid file name to let it know what is the grid definition is. And the second thing should be the data itself. And it should open the data. So it is still busy with the importing part. And there might be time-dependent slowness with the HPC clusters. It is not directly related to your tool because of the time of the day. If a lot of people are accessing, you can have some slowness. Yeah, go ahead.
Is there any way you can increase, like zoom
Yeah.
in on that screen for people in the room
Yes.
who can't read it?
Thank you so much for that point. Let me first find where that interface was. Appearance. Where was the zoom here?
Also, maybe while presenting Orhan, I would keep the file explorer on the left side collapsed, just so there's more code on the screen relative to the rest of
Yeah.
Jupyter Hub.
Yeah, thanks so much for that point as well. Yep. Is it good now? Nope, little bit more. How is it? Okay. Yeah.
You could
Thanks so much
also
for that.
go into full screen mode.
Yeah. Full
you click
screen
view
with
at
the
the-
zoom or
If you go to the top of the screen and click view,
this one?
yes. And then there should be an enter full screen on there.
Okay. Good. Yeah. Anyway, so at least we can see the code from the very back of the room, right? Okay. Where were we? The only thing I don't like here is with the zoomed in version, I cannot see if it is busy or idle, but that's just fine. We can see that here. Is it still running? Again, this is definitely an HPC cluster thing. I think we don't have anything alternative to do this. Philip, do you have your HPC cluster, maybe Derecho or Casper?
I'm trying both. They're running a little bit slowly for me right now as well.
Yeah, I think because of a lot of people maybe spinning up some okay, it is going through now. Then we can go with this opening dataset step. Grid file name is not defined. Yeah, I didn't execute this, I think. It is running. While it is running, we can, I think, type the next code. What should that be? If we have a data set, then we can have access to variables of interest in that data set, just like this. Let's look into maybe 2-meter temperature, this one. I don't have a lot of like story concerns on this one. It is just going to be 3 lines of code to plot. So just 2-meter temperature. Then I have that one. I think I have multiple time steps here. So I should do this to access one of the time steps. Then since I have my data array of interest now in my hand, I'd like to access the plot accessor here. Then if I am having access to plot accessor, and actually the first one could be directly the default plotting function. So this should just work. I am not playing with any color maps as of now, not anything else, just plain plotting of the data array. It looks like it's gone through, even though I cannot see it from here. Just run this. I think this warning we are giving right now is probably irrelevant because I am sure the number of faces in this data set is no more than 650,000 ones. Yeah, this is the 2-meter temperature global data. From now on, you can do anything. Like you can play with the color maps, you can subset and everything else, but we will be showcasing them already throughout the tutorial. So far, just 3 lines of code give the scientist the capability to plot unstructured grids. One great thing here is we are visualizing the actual native unstructured grids, not regrading under the hood, nothing else. So the actual unstructured grids is being visualized here. And because we are receiving a lot of questions about if it is only applicable to MPAS, I'd like to emphasize one more time, no, it is not. If you have chem spectral elements, you could do the same 3 lines of code without changing anything other than the data file locations. So you could do that with the E3SM data sets as well, like script, maybe Exodus file extensions. The interface, 3 lines of code should have been the same. You wouldn't need to change anything. And I think this is one of the power strengths coming with UXarray. We are really glad with. So any questions so far? Again, we will be playing with all of the global data being subset into some regional data of interest and color maps and everything else. But so far, is there any question about this plain plotting? If not, maybe I can, let me see if I am not sure. Let me see if I can find a horizontal bar here to move this plot. Forgive me, I will be zooming out at this point, not to show you a code, but to show you a feature of this plot. So we are working with under the hood HoloViz visualization package. That means we are capable of visualizing any HoloViz supported things, which gives us a lot of interactivity as well. It is not the actual focus of this plot, but I would still like to show you how interactive that could be. So if you have such a global map, you can always reset it. You can zoom into a rectangular area of interest. You can turn. Why is this looking like this? Because it is not dynamically rendering for this type of plot, because it is just a default plotting method. We will be showing you some more interactivity. You can reset anytime. You can wheel scroll as well, and you can also hover. Since I called the default function here, it doesn't show me the data values when I am hovering around, but if you made hover over argument true, it could show you actual data values whenever you are hovering over the global map. So that's the interactivity coming from, and under the hood, it is making use of bokeh package, and there is also support for matplotlib, so you can switch between bokeh and matplotlib. I think unless we have any questions over Zoom or in the room, I think we can move on, because we have a lot of more really impressive, I think, visualizations today. Yeah, go ahead, please. Definitely, yeah. And I'd like to show some of them through the subsetting notebook of today's, because, you know, before and after subsetting, you can run analysis functions with UXarray, and it can give you the global, for example, mean, or the mean of the regional area that you are interested in. Yeah. Yeah, I think you are talking about if we subset into a region of interest in UXarray, would that account for the analysis functions like averaging? Yes, and I'd like to show that to you throughout the tutorial. We have a subsetting example, and in which I'd like to show you how subsetting would be really beneficial with a visualization of really big data sets on the region of interest, or how that could give you analysis operators for globally or regional applications. And can we help people with maybe running Mike's way? Is there such an opportunity for us? Because the questions are really giving me a hard time to hear, and I think it is the same for the Zoom people as well. And if it is being recorded, that would be really helpful for other people if we can run mics around the house, around the room. Okay, so let's get rid of this 3 lines of code from scratch thing. Turning back to our, I think I should leave the full screen, which gave us almost, I think, nothing. Turn back to tutorial. The next thing should be why UXarray. I think we touched some of them, but I would still like to show you. This is a section from the cookbook I mentioned in the very beginning of the tutorial. So first, UXarray is, one more time, not focused on just a single unstructured grids. That's one of the biggest challenges in the unstructured grids research from my perspective as a developer. There are a lot of different unstructured grid models, different communities or research institutions are creating and sticking to around the globe. So there is the MPAS, there is ChemSE. I like to emphasize MPAS is, I think, one of the earliest with UGrid that we supported with UXarray, and it is one of the strongest supported grid formats, which Philip is going to cover today, why it is one of the strongest. But MPAS is not only one grid format that we are supporting. We support a lot of others, which I will be covering through the plotting API section of today. That's one strength. Other strength is, while we are supporting those different grid formats, we are supporting them in the same interface. Just like I mentioned that in the previous section, you can use the same exact visualization functions or data analysis functions for various grid formats without changing anything. I think that's a great strength with, especially with a tool on unstructured grids, which was not the case, as far as I know, before the UXarray. We adhere to UGrid specifications, so everyone else can learn the UGrid conventions, then they can comprehend how we are converting MPAS or other grid formats into UGrid and turning them back if we are exporting any MPAS again. So rather than asking people to learn a lot of those different unstructured grid formats, we are just asking people to, hey, let's come together around the UGrid conventions, and if we can all understand the UGrid conventions, and we can speak the same language on supporting different grid formats. That's what we are doing here. The third thing is, I think I already talked about this. We inherit from XArray. So if you are an existing XArray user, you would love UXarray because it is almost the same. So that was one of the biggest community asks to us in the very beginning stage of UXarray development. A lot of community members asked us, hey, I have a lot of XArray workflows already. Rather than asking me to change a lot of things, could you provide me something like, I can just change the importing line, like instead of import XArray as XR, let me just do import UXarray as UX. Then the rest of the code should do similar things, if not all the same, you know, and that's what we are doing here. The built-in XArray functions are already provided unless they are giving problematic results for unstructured grids. For example, there is a built-in averaging function, mean, with XArray, right? You are able to run mean function of XArray without any change with UXarray. And there are also some functions which would require some changes because of the unstructured grids specification. For example, Philip, Rachel, you could help me. I am just getting my brain frozen. What was one of those functions, Philip, we had to overwrite for unstructured grid purposes?
So not necessarily, I mean, we already mentioned the plotting one. That's the primary one that we overrided. We extended certain ones, for example, like the index
Integrate.
selection.
Yeah, I think integrate as well, as far as I can remember.
Yeah.
So whenever there is a built-in XArray function that should be implemented in a different way to account for unstructured grids, we are overriding them to provide the community with the same function name for unstructured grids. And there are third category, which is there was not a function in UXarray. We are implementing them for unstructured grid purposes, like subsetting, for example, or remapping. So that's what I'd like to say for, yeah, who? Oh yeah, Philip, go ahead, please.
Yeah, I'd like to mention as well that a lot of the overwritten functions are on the internal side as well. So managing simple things like keeping a reference to what grid we're working with required us to overload a lot of existing like private functions that were part of Xarray. So thankfully, it's not something the user needs to worry about. We try to make it as seamless as possible, and there's, I would say, a very low learning curve for getting adjusted to the changes.
Yeah, thank you so much, Philip. I am a little bit speeding up because of the timing. We already talked about this standardization of different grid formats. Yeah, our data structures are first inherited from Xarray data structures. Second, they are optimized for performance. We are still working on performance because of some sparsity and like connectivity, which could take a lot of memory consumption actually. We are focusing on them throughout the internship we are doing with Rachel, and we will be focusing on them afterwards as well. Yeah, and because of all of these, we have strong interoperability with other Pangeo or scientific Python ecosystem packages like Xarray, NumPy, Pandas, Matplotlib, Holoviz for visualization. That said, is there any question? Okay, let's move on to next one, which is UXarray and MPAS. Philip, the stage is yours.
Yep. Can I share my screen as well for this one?
Yeah.
Okay.
I am stopping mine.
And while I'm presenting this, Orhan, I think Rachel may have already mentioned to you, can you look into the permissions real quick for the, so not the demo notebooks library or directory, but the one right before it. So Rachel can update you on that, but let me get my screen shared. And yeah, thank you for the great introduction, Orhan. And you already covered a couple points here that I wanted to mention. First of all, is my screen sharing okay?
Yep, we can see it okay.
Okay, perfect. Yeah, so UXarray and MPAS, as Orhan already mentioned, MPAS is our second most supported grid format. And that's kind of obvious because our number one, we're written around the UGrid convention. So that's naturally going to be our most supported format. And we can see here on the right from these tables, the first column, so both of these tables represent what variables such as coordinates and connectivity we're able to load in and represent in the UGrid conventions. So the coordinates, for example, this could be the corner nodes or the centers of each element, such as the edges and faces. And we can see for MPAS, we support loading all of these into the UGrid conventions. And for connectivity, there's a few that are listed as no, and that's mostly we haven't figured out the best way to represent them in the UGrid conventions as of right now, but we support parsing almost all of the connectivity that is provided through an MPAS grid. And
excuse me, Philip, could you put it in slideshow mode?
Oh yeah, sorry, it might be a little bit small. Is this a little bit better? Perfect. Yeah, going back to here. So as I mentioned, MPAS is one of our most supported formats. And when we load the data into the UGrid conventions, we do a little bit of processing of the connectivity and coordinates to get them to be in the UGrid conventions. And thankfully, the processing is pretty minimal. It's really as simple as going from 1 indexing to 0 indexing, and then also standardizing some of the fill values. So instead of using 0 as a padded or fill value, or we end up using a arbitrary value such as -int64. And this is something that as a user, you won't even really notice, because as you'll see in a couple of the next presentations that we give, all of the interacting with connectivity, whether it's for plotting, for analysis, for basic data IO, it's all handled by our grid object. So the majority of things are abstracted away, so you don't even notice these changes. And on the bottom left here, we have a quick plot just showcasing the primal and dual mesh that was visualized using UXarray. And both down here, we have a couple links. I can actually show those just real quick. I'm not going to go through them in detail, but this is one of the visualization examples that we have. And you can see it's actually interactive. So we can zoom around, and we'll see a lot more of this during today's presentation. And I don't think we've covered this yet, but we have a section that goes over the supported grid formats. There's a small paragraph here on MPAS, and you will be able to find those tables that I had listed in the presentation as well. So that's all I wanted to cover. And lastly, I did just want to mention, if you go into the slides and click on UXarray and MPAS, we have a workflow example as well that goes over more in detail of what coordinates and connectivity variables we parse and what changes were made to them. And this should give you a pretty detailed guided example of how to load in either the primal or dual mesh and do some pretty basic analysis operations. But I don't want to duplicate any of the content we'll be going over today. So this will all be covered throughout today's session. And I think now I'll pass it back to Rachel in the room, and we can present a quick comparison of UXarray versus XArray.
That's good. Thank you, Philip. So I'll briefly go over like the similarities of UXarray and XArray. So I personally I am more familiar with XArray. So when I can give like a firsthand comment about like how similar it is from XArray to UXarray. So basically, this is also like available on the cookbook that's publicly available. So the same things that we have to do will be also like be importing the UXarray package. And all we have, the first thing we'll be demonstrating here is about the UXarray common functions. So we'll still be like defining like the file path and also like what the which file are we looking at, and we'll load the file through XArray, and we'll see like based off on the dimension, we can see this is like a structured grid, so it's on lat long grid. But if we compare to using UXarray, we'll also like be doing the same thing. The only difference that we have to do is like to load the grid file. So this is like an additional step we needed to tell UXarray which grid we're on, and just doing the same thing by open dataset. And we'll include the grid file and also like the unstructured data, the data on unstructured grid. And we can see it's based on the dimension shown here, it's on n phase. So we know this is like the unstructured grid data. So as now we'll be showing like how we use UXarray and like how similar it is to XArray. So in XArray we'll be so we'll define XArray as XRDS for an XArray dataset, and we're specifically plotting the variable PSI. And what we'll do here is just do dot plot and specify the figure size and also like what color map we're using. So this is for XArray workflow. But if we were to this is like the only single figure. The second example we'll show here is like how to plot multiple subplots using XArray. So we'll using matplotlib, and we'll specify like we're plotting two figures in two different rows, and also like this figure size, and also like there's two different maps on different color maps. But for XArray, it's basically the same. So rather than calling XRDS, we'll be calling UXDS, which is an unstructured grid dataset, UXarray dataset. And we'll just call dot plot as well to plot the figure here. And as Orhan was mentioning earlier, UXarray mainly have default plot as using HoloViz. So that's why there's this interactive plot here. And rather than calling fixed size, the only difference is we'll call width and height, but still CMAP, this argument is still the same in UXarray. And if we were to, one argument that UXarray has is to deal with the anti-meridian issue, where if we set anti-meridian as false, exclude anti-meridian as false, like we can do, UXarray has this functionality of identifying the different unstructured grid along the anti-meridian, and they can select what is on the left and on the right side of the anti-meridian and resolving that anti-meridian issue. However, it's a note to make is that if we have exclude anti-meridian set as true to deal with this issue, then there will be a loss in performance where it'll take more time for UXarray to process the data, like which grid is on the anti-meridian, and then they will sub-select those that are included in that region of selection. So, however, so yeah, that's like one function that UXarray has. And if I reset this, it will show the figure.
Just one quick question for clarification. So we probably only need to worry about that exclude anti-meridian option if we happen to be looking at something that's over the international date line, basically.
Yeah. But yeah, I just want to highlight that function that's there. So UXarray has this power. But one thing different for plotting multiple subplots using UXarray is that rather than specifying using like matplotlib plt.subplot, well, it's more like a dictionary for HoloViz. So we'll just do like the first plot and then just use a plus sign to specify the second plot. And then at the end, we'll like define the orientation, whether we want it to be like on the same row or in like a different, on like a same column, which is shown here. So basically it's the same as what we do for UXarray, for Xarray, sorry. But yeah. And last but not least, there's also like with the use of HoloViz, we can do a combination of both Xarray and UXarray in the same figure. But more details of this is more is in the documentation of HoloViz. But in this cookbook, we also have like a simple example to show how that could be done. So it's same as UXarray plotting multiple subplots. So we'll just call the Xarray on HoloViz plots and also UXarray as the regular plots, then we can still do the same. So as shown here, so we can see in this is one figure where the upper subplot is Xarray with HoloViz, and the bottom plot is UXarray, which I have to scroll down to show. Yeah, so this is like the functionalities of what you can do doing like subplots for UXarray and Xarray, and also like how similar it could be when it comes to plotting for Xarray and UXarray. Yeah.
Thank you so much, Rachel. Any questions so far? Go ahead, please. Thank you.
You showed a subplot with only two. What if you have more than two? How do you specify in UXarray? Is there an example for that? You have like a 2x2 figure instead of like a 1x2.
We don't have an example right here, but I think like it's something we could do. By oh yeah, Philip, take it away.
Yeah, it's the same convention that you would do here. So it can be a little bit confusing because HoloViz, they do, like, as Rachel mentioned, the addition and multiplication to indicate whether you're creating a subplot or an overlay. So for example, if you had 4 plots, I think you mentioned, you would simply add together those 4 plots. And then that line down there that says dot columns 1, that's telling us we want a single column. So if you did 4 additions, you would have 4 plots stacked on top of each other. And you can also pass through a rows parameter as well. This is all in the HoloViews documentation, which we can share. But I know that in one of our user guides, I think we'll get to it towards the end of today in the remapping one, we have some of those multiple stacked figure examples.
Thank you, Philip. Any more questions? Okay, how about Zoom? Are we good? Okay, let's move on.
Or sorry, I did have a question.
Yeah, go ahead, please.
Is there any way, like, will there be support for plotting with Matplotlib? Because I'm more used to that. And is there like maybe a way or to output it, the lat long variable?
Yeah, I will be covering that in the next section.
Okay.
How you could do that, and yeah, we can check one more time if that's an answer to your question. If not, maybe we can talk about what should be there.
Right.
Any more questions? Okay, let's move on. So, should I first start?
One thing as well, Orhan.
Oh, okay. Is it? Okay. Yeah, good. Okay. Go ahead, Philip.
Yeah, I just wanted to mention, if we're presenting any other notebooks, there's a presentation mode as well in Jupyter that lets the text be a little bit bigger. So
Okay.
if we do get to any more notebooks, it'll be under View, Appearance, Presentation mode, just so that we have it.
Okay, so okay, let me first cover this and then we can check that in this
Yep, just wanted to let you know.
space. So now we are at this point. First, we will be really quick introducing the plotting API of UXarray so you can know how to access plotting functionalities from different data structures like the grid object, data set, or data array at any time. Then we will start looking into some like advanced topics like subsetting, some interactive visualizations for time series analysis, and remapping functionality of UXarray as well. So now, I think for this one, it's going to be through the cookbook material. So if you go into cookbooks, the plotting API is here on the left-hand side, the UXarray visualizations starting point. So plotting API, I feel like we have covered a lot of things here, but I'd like to still emphasize first. Is it readable from the maybe back of the room? You don't have to read these individual functions, but at least if you can see the diagram, that would be great. I think this is the most I can do. Let me see. Yeah. So this is a crowded diagram, but I'd like to give you some key takeaways about this. So first thing is the supported formats we talk about. Regardless of the grid format you are inputting into UXarray, we are getting them and changing them into a unified representation model in a very UGrid-like convention. Why I am saying not UGrid, but UGrid-like? Because UGrid doesn't have some of the connectivities required, but we are also introducing them because of their use. So I think it would be fair to say we are covering all of the required UGrid convention parameters and putting some additional on top of it. Philip, would that be a fair statement? Would you like to add anything there?
Yeah, that's completely correct. And honestly, the main reason we've kind of added and extended the UGrid convention slightly is because MPAS actually technically supports more connectivity variables than are described in those conventions. So you could almost think of our UGrid implementation as being inspired by MPAS in certain areas.
Yeah, thank you, Philip. And moving on, that was the first key takeaway. The second key takeaway about this diagram is, as we mentioned before, UXarray have key data structures. Data array and data set are common, like coming from the XArray. If you have a netcdf file, if you read that in, you have a data set, right? And if you are having an interest in one of those data variables coming from that data set, it is data array. And what adds the grid topology information into UXarray data structures is the grid object itself. So grid object recognizes the unstructured grid geometry, and the rest is keeping the information about the data associated with that grid topology. And for each of these data structures, we have a dot plot accessor, which means if you would like to diagnose your grid geometry itself without looking into any data, you should be accessing the grid objects dot plot accessor, which means grid dot plot dot function of interest to visualize. Or if you are interested in actually visualizing your data, you should be calling most of the time the data array dot plot visualization. I don't know. I don't think we have any data set visualization functions for now. And most of the time, the scientist's purpose is to visualize one of the data arrays. So we have several functionalities here that we have defined. And one more thing here, at any time, if you are looking into data arrays, you have still access to grid object, which means UX data array dot UX grid can always give you the information about the grid geometry. From there, you can still diagnose your grid geometry at any time throughout your workflow. But most of the time, you as the MPAS user would be using one of the visualization functions from this data array. We are coming to key visualization capabilities discussion here. So you have, you can see hollow views here in the blue color code and other things in the green color code. I'd like to give you why these are color coded. These are the native functional visualization functions that we are getting from hollow views, and top of them, we are implementing our own unstructured grids specialized visualization functions. So if you would like to run any of our visualization functions, you don't have to directly deal with the built-in definitions of hollow views, but you can if you want. What that means, you are using some of the arguments from UXarray, plus you have still access to function signatures and arguments. Like you can adjust the visualization parameters from the hollow views functionality as well. Or if you don't like to deal with the hollow views functionality, you would like to export some data structures from UXarray and would like to visualize them with your own Matplotlib package, you can do that with the help of these green functionality. So okay, I have a Zoom interface showing up here, but it is good. It is not showing up there. So you can see this green parts. So if you would like to visualize unstructured grids with your Matplotlib imported Matplotlib package, you can export unstructured grids from UXarray through one of these poly collection or line collection, and you can still use Matplotlib. But we are not recommending that because there is no need actually. The HoloViews visualization package itself is a suite of packages actually, and under the hood, they can still support the backend of Matplotlib. If you just pick the backend to be Matplotlib through UXarray visualization functions, you are still able to generate Matplotlib plots. You don't even have to generate these data structures and export them out of UXarray. That's not what we are recommending, but if you are still interested in getting those data sets out of data structures out of UXarray and using Matplotlib functions, built-in functions themselves, you can still do that. But we are actually more focusing on functionality here because HoloViz seems to be scalable with their visualization functions, and they can support a lot of different data structures. So, and they support a lot of strengths, like they can support directly connectivity information. You don't have to do anything to deal with the connectivities and things like that in the as you would do in the Matplotlib case. So we have rasterization functionalities. If you have a really big data set, but you would like to still see the global data, or we have some actual vector plotting options like polygons, for example, if you would like to not compromise any data fidelity. I'd like to show these through the subsetting example. So I think this is everything I'd like to tell about the Why cannot I escape? Okay. Any questions so far on the diagram, at least, of the plotting API? Go ahead, please.
So things like, or library packages like CartaPy, for instance, those are entirely matplotlib based, or are they, or does CartaPy, would CartaPy be able to link in with HoloViews? Just thinking because, you know, with a lot of the WRF plotting scripts that I already have use CartaPy and matplotlib, so, you know, switching into a HoloViews framework could do that. I'm just wondering, in that sense, like kind of how much I'd have to totally revamp all the tools that I would have, but
As far as I know, HoloView's suite of packages have very strong CartoPy projections support, so you can definitely use them. Some of them might be still missing, like vector polygons might be missing projection supports, but they seem to be working very well on their functionality and the feature requests from the community, which we experienced before for the UXarray purposes as well. They are quick to resolve things if you request something. So I think they would probably be keeping to add those functionality in the future as well. Philip, please feel free to chime in and add your comments there too.
Yeah, so it's HoloViews, well, HoloViz, their stack of tools. They have a package called GeoViews, which is specifically made for working with geographic projections, with geographic features. And I believe in the subsetting notebook, and at least the interactive notebook, will show off how we can have like borders, coastlines, state borders, those different types of geographic features. And I believe, I don't know if any of the notebooks we have here, but our point visualization does support CartoPy projections. So if you're looking for like a Robinson or orthographic projection of your data, we have support for that.
Yeah, thank you, Philip. I think we are at a good point now that we can jump right into some of the actual real-time visualizations. The first is going to be subsetting. I'd like to show this to you, but before then, I'd like to ask if there is any more questions.
So does UXarray have all this statistic package like you do and bias correlation, those kind of things?
We are implementing some of them ourselves. And also, as we mentioned before, we have already built in XArray statistical functions that come into UXarray function signatures. So I don't know when you say all of those statistics, but we can talk about maybe individual functionality. And if we feel, unstructured grids would take a lot of help from that function, we are more than happy to either implement them ourselves or maybe work with you, work with the community members to how to implement them into the UXarray package. Go ahead, please.
The UXarray have the function to plot the vector field, like the quiver or?
That's a very good question. Quiver visualizations are you talking about? Quiver visualizations, right? That's a very good point, and we are going to work on them soon because for flow analysis, I think Quiver and a lot of other like curly vectors, for example, would be great additions to UXarray. They are in our agenda, not in the roadmap yet, but I think I can envision to work on them in the upcoming year.
And also about the gradient of the field, like the temperature gradient field, still have the function to do that for the unstructured mesh.
Yeah, we have some gradient functionality already, and we will be working on some advanced gradients functionality as well. Actually, your questions remind me of another, I think, important point for the sustainability part of the UXarray. So even though our team is working really hard to implement all of these functions, it's kind of a community effort. So for example, I think it was gradients that we worked with. I don't know if she's here, but Amanda Justine from, I think, as far as I know, from MCube. We worked with her to introduce gradients. Amanda had gradients for MPAS only. we worked with her. She was very helpful, and Philip was great on understanding the problem and understanding the MPAS specific implementations and generalizing them to our UGrid convention way. So just like that, we are eagerly looking for people. Maybe you may not have time to implement them into the UXarray, but even if you can show your workflows to us, that would be really helpful to generalize them. For example, if you have a functionality that would work only on MPAS, show them to us, communicate with us, and we can be happy to work on them, to generalize them to UXarray so that not only MPAS folks, but also other people could benefit from them. So we are, again, eagerly looking into these kind of community engagements to make this more sustainable and more beneficial for the whole community, if that makes sense.
Thank you.
Thank you so much for your questions. Any more questions before we jump into subsetting? Anything on Zoom, Rachel? Nope. Okay, let's jump into one of the real-time implementations now. So this is subsetting, and I will do my best to explain why and where subsetting could be really useful with UXarray. This time I have this thing imported for. I think we should be good. I mentioned this before. CM Ocean is just an optional like beautiful color maps package. You don't have to do this, but if you want to find some ocean purposed ocean analysis purposed color maps, it is here. I am going to be using thermal for this because I will be using 2-meter temperature for this demonstration. And I will be using the global data set for a specific purpose here. So this is the one I showed you before in the 3 lines of code visualization. That was the very first thing we did today. This is the 30-kilometer diamond data, which has, I think, 655,000 faces and around 1.3 million nodes, since it is an MPAS. And globally, let's get started first. This is the dataset opening function we showed before. And if you look into the data array of interest, which is again the 0 time step of this 2-meter temperature, it is here. The dimension here, I think I can show UXgrid object to you. Yeah, number of faces is 655,000. This is not a like monstrous big data, but it is still something, especially for vector polygon kind of visualizations, which I would really like to show you some things there. And this is all of the connectivity information you can see here, and the regular geometry related elements here that are associated with the grid topology. And when you look into plotting such a global data, we recommend using rasterizations because of the performance it could give you. So I will show you the 44 seconds here execution time. Some of them I am pretty sure is coming from the HPC cluster things, but you can give a try to this on your maybe local laptops to see the actual execution times. But if you were to run that one more time, I think it should have been much more faster. This is nothing special. So I am using the thermal color map here, and I am rasterizing the polygons. What does that mean to rasterize the polygons? It is meaning, let me zoom somewhere here. You don't have anymore the hexagonal MPAS structure because you are rasterizing, and however the rasterization algorithm works, it is breaking the hexagons into some rasterized rendered images, right? So this is rasterized polygons. What if you wanted to not compromise data fidelity and you wanted actual vector polygons? In that case, we would recommend to use subsetting functionalities of UXarray. So instead of focusing on the entire globe, if you can find a region of interest, you can go ahead, subset your data into that region of interest. Then you can even execute actual vector polygons on that region of interest. So for that one, this is nothing more than geographic features. So, okay, I'd like to show this to you as well. Again, no change to data. I'm just showing the coastlines, borders, and states for better maybe readability of data. It is here, but it is still the rasterized data, as you can see here. And that's one good benefit with the high-level HoloViz based visualizations. If you are creating different plots or different plotting features, you can multiply them like this, and they can show up in the same exact plotting. So I would like to show you one more time. This was the regular plot. If you just multiply this with the features you have created, it can right away at the geographic features here. And you can do those multiplications for a lot of different plots, or you can also do additions to show those plots side by side, or one in the upper, one in the lower as well. Anyway, so that's not the actual focus of this subsetting. I'd like to show you one subsetting feature. So this is one of the regions of interest. So we are looking into a rectangular area of west 105 and 80 longitudes and 28 to 45 north latitudes. How you could subset any UX data array is like this: data array dot subset dot the subsetting function of interest that can be either bounding box or bounding circle or nearest neighbors. So in this one, we are using bounding box. You can see some like imperfections here because this is the easiest bounding box we could do. We are still working on precise bounding box algorithms, but this is still, especially for visualization purposes, very useful for the UXarray user. So in this one, I'd like to emphasize one more thing to you. At this point, you have a brand new grid where you have actually only the region of interest. You no longer have the rest of the global data. You just are focusing on the region of interest, and the data itself is just that one. And I'd like to focus one more thing as well. The function, the visualization function is changing from rasterization to polygons here, because after this subsetting, we are now able to perform very well with the actual data fidelity without compromising any resolution there. So these are the actual MPAS hexagons because we are using the actual vector polygon visualization function here. Line width is controlling the colors and widths of those hexagonal grid geometry elements there. I am still adding some features here. I'd like to show you with this one. I'd like to zoom in and show you the actual MPAS structure. So this is the actual data. There is no compromising of any data fidelity in this one. I am not sure if that's visible. So let me turn back and maybe do zoom into some darker color areas. I think it is visible, but let's get rid of this line width for now and run that one more time. Yeah, it's going to be crowded with all of those hexagonal elements, but I think we can zoom in one more time just to show you. Okay, yeah, this is the actual MPAS structure, that you are not compromising any resolution or any things to the rasterization. So after the subsetting, you are able to do this. There are some more cases where you can still do vector polygon visualization. if you have really, really small, low resolution, you can still do it in the global data, but most of the time, the researchers' interest is few kilometer resolution with some region of interest. So I think this would be great on those kind of things. And I think we can. Philip, go ahead.
Yeah, no, I just wanted to quickly mention, you were going over how you can call like dot bounding box, dot plot. And I just wanted to mention to everyone that our implementation is very close to UXarray in the sense that we follow a fluent interface, meaning that you can chain together multiple different methods. So for example, you could do a data variable access followed by a bounding box, followed by a gradient or a mean operation. And you're able to do those all fluently in one line.
Yeah, I was just gonna show that to the audience actually. Let's first run this. This is the, as you can see here, I am assigning this subset region, the grid into one brand new variable, which is UXDA underscore subset. So this is my actual data array, the global data. This is the region of interest data array. So this is the mean for the global data. And if I add this similar thing to here, and instead of the global data subset here, so this is the region of interest where we put it here. Oops, let's reset this. Yeah, so this region of interest has a mean of 300 kelvins, I think, for temperature, but the global data had 288. If we were working on a region of interest like this, it would be much cooler. But the great thing here is we are generating a new grid after the subsetting operation. Then we are able to run analysis operators on that one as a new grid, which gives us the actual data. And again, since we are not breaking the actual data resolution here, we are working on actual data statistics. I think it was your question, but please follow up on this if you have anything.
Yeah, this was related to my question before. So if your grid is not uniform, let's say the center of your domain has more data points, then would this mean function be wrong because, or is it taking into account the size of each grid cell of your data?
That's a very good question. So this one is just like no cell areas incorporated into calculations. But that's going to be great. And Philip, is any one of us in the team currently working on it? As far as I can remember, no, for the time.
For the bounding box functionality, right?
Weighted averaging, yeah.
I think we are. It's just it's been pushed back because there's just a lot of helper functions that go into it. But I think that's something that Rachel might be able to help out with this summer. So we're getting there in terms of weighted functionality.
So, but that's also a question of the global mesh. That when you take a mean, you have to the area times the value.
Yes.
And divided by the total area.
Yeah, that's right.
This is a critical thing.
Area-based weighted averaging is going to be in our function signatures for sure. As of now, it is just built in naive averaging.
Because when we first released MPAS with the variable resolution, people using variable resolution meshes, a lot of people were making that error, just doing an average of the values as opposed to a weighted thing.
Yeah.
This is a critical thing to have.
That's a very critical thing with variable resolution data. And I think, just like you did here, I think we have to emphasize this everywhere. Yeah, I agree with this. Because probably there's going to be a lot of confusion even from now on in the future in the community because we are not used to use, right? So variable resolution data.
Yeah, and just to kind of tag along with that, I would encourage the area weighted mean and area weighted statistics to be the default.
Yes.
Because that's
Yeah.
what people I think expect, and that's the scientifically correct thing. And there might be some side applications where you don't want the area corrected or area weighted mean, but you should have to explicitly
Make that.
choose that
Yeah. Yeah.
so that you don't wander into myths about your data. I guess another question. So the UXDA underscore subset variable, if you were to do UXDA underscore subset dot grid, would that show like how many grid faces there are
Yeah,
and things
yeah,
like
yeah.
that as in for the global data set?
Oh yeah, because it is just this the same data structure, not the same data, but the same data structure, the same grid object that has all required information. And I'd like to show you really quick. Where was it? Subset dot UX grids you were asking about.
Also,
Yeah, it
real
is here.
quick on that point as
Number
well.
of faces is just like slightly less than 6,000. And Philip, before you go on, I'd like to ask maybe you or Rachel, that was really great point about the area weighted area. Can we maybe initialize some Google Docs that we can keep track of these kind of questions for like development purposes? Philip, go ahead.
Yeah, on the point of the new grid returning. So when you perform a subset, internally, we do a grid-based index selection based off the connectivity that we have stored internally. So when we do the subset, the data array that's returned has a new grid object, which only contains the elements that were returned from the query that we did internally. So you can start off with a global grid, do a bounding box, and then you can go ahead and save it to a net CDF, and you would only have that region of the grid. So this is not just being done at the visualization stage. Hopefully that answers your question as well.
Any more? Yeah, go ahead. Yeah, go ahead.
Just for posterity, I'll just say that's a very nice feature. Yeah, especially coming from the WRF framework where that doesn't really exist so nicely. This is a really nice thing. So
thank you so much.
We have a question online
please,
as well.
90 minutes is from one perspective long, from another perspective very short. So I am pretty sure you will have questions and maybe feature requests afterwards. Please reach out to us through maybe GitHub discussions, GitHub issues, or maybe things like that. We would be really happy to, follow up on any of these things. Go ahead, please.
Or to be more picky about the mean, if you're gonna do the mean like correct by the area size adjusted, then also the vertical mean should, be weighted by density or something.
Yeah.
So if you really want to be a scientific framework.
Yeah, thanks so much. Yeah, I agree. Philip, I think I gave the core motivation of the subsetting. I'd like to really stop at this point because you have really impressive visualizations with you. So please go ahead and in the rest of the time, please show them.
Sounds good. How are we doing for time, by the way? 30 minutes, I think?
We are doing very bad. I am taking that on myself. So we have, I think, just 4 minutes left.
Oh, okay. Let me go through and showcase these examples for everyone.
I think not only for area weighted averaging, but also for timing, I should work on. Yeah, I am doing a very bad job with that one.
Okay, so this notebook will all be shared with you after today for those that don't have access to Glade. But just for the sake of the time, I want to showcase these examples and you can dig into the code afterwards. So here we have a couple interactive plots, and by interactive, I don't mean panning and zooming. I mean visualizing multiple variables across different dimensions. So the data that Wei provided for us is a regionally refined continental United States model run. And here I'm plotting the 2-meter temperature across time steps. So I'm just moving the slider right here, and we can see as I move the slider, it's updating the time step right here, and we can see the evolution of the variable through time. So this is an example of the size is fine for everyone in person, right? I hope it's big enough. But you can see here that it's changing, and this was all generated using a pretty simple code block with UXarray and hollow views.
And for this analysis, if you have multiple diagnosis or history files, you can give their pattern into UXarray. It can read all of them in the same line of codes.
Yep.
Open multiple file datasets.
And it can also use Dask as well. So internally, these would be stored as Dask arrays, and you could do chunking across time dimensions and other ones too. The next one, so we were just going over the subsetting functionality. This is a bounding circle over it's roughly around Fort Collins area. So it's between the Wyoming and Colorado border. And I chose this because there was some interesting behavior with the 2-meter temperature. You can see going through the time steps. I'm not a scientist, but it looked very jittery at the initial steps, and then it smooths out afterwards. So I thought that was a pretty interesting case to show. And this is a bounding circle with a 1.5 degree radius. So pretty zoomed in compared to the entire data set. And I also have another example here. So Wei provided us with a couple reference PDFs of some NCL code for looking at total grid scale precipitation and radar reflectivity over a region of interest. So here we have a very basic workflow where we do a bounding box, and then we plot these two variables side by side. So if I go through the steps here, we can see as our reflectivity moves across this region, we can see on the left side that the total precipitation is increasing and accumulating, and this is all taken from the model output that we had visualized across time. And here we only have about 23 time steps, but if you're working with much larger, maybe multiple years worth of monthly data, you'd be able to do the same thing with really no code adjustments needed. May take longer to actually execute, but you would have the same type of interface where you can scroll through, see the change across time. And I wanted to also cover this dashboard. I think we don't have time for it today. Orhan, what do you think?
Please cover that really, really quick, because it's also, I think, very important for multi-data variable time series analysis for people who are using MPAS. I think you should be definitely showing that really quick.
Okay. So, I think I need to add a quick line of code right here.
And the data Philip showed you was hourly data from one single day only.
Yeah. So let me get this one working here. So looks like something actually changed with it, but here we have a very basic dashboard of looks like our features are missing, but that's okay, where you can choose and switch between different data variables, and you can go between time steps. If your data has a vertical dimension, you can also switch it with these sliders. Yeah, I know we're running a little low on time, but this dashboard is more of if you're like in the exploratory stage of looking at whatever data set you have, you can go ahead and switch to, let's say, vorticity, for example. So this is going from, it also supports different types of color maps. So I think for vorticity, it might be better to use like a delta color map. And then if we switch through time, maybe I didn't choose like the best data variable because it's, yeah, this one's a little hard to see, but with a little bit of tweaking here, you can start to see, and you can adjust your color map. Here is the reflectivity that I was just showing you all. You can switch it across time. And this is also interactive, like the one we had earlier. So you can zoom in, change your time steps. There's a little bit of lag here and there, which is expected because we're dynamically calling the UXarray functionality. So there's a slight delay. None of this is pre-computed. The examples above were all pre-computed and stored as a dictionary and then rendered like this. This dashboard, the neat thing is it's all being done in real time. And there's pros and cons to both methods. If you care about the most responsive types of plots, of course, it's worth doing the pre-computations before. But if you're just exploring your data, it makes sense to just lose a little bit of the response time to be able to quickly switch between time steps and data variables. So I'll make sure we'll share all of this after today's meeting, but I don't want to go too over because I think it's about lunchtime, and we all know
thank you
hungry
so much,
people are
Philip.
not happy people.
Thank you very much, Philip. Could you, okay, you stop your.
Oh, did you need me to keep sharing?
That's okay. So I think we couldn't cover the remapping part from this tutorial. That's fine. You can reach out to us. UXarray have some initial remapping functionality on unstructured to unstructured capabilities. We are going to work on structured to unstructured and vice versa, because we know there is still use cases for them as well, even though our actual motivation is to natively work on native grids rather than needing to regrid them. That's one thing. The other thing is like reach out to us. We can clarify anything, or we can work with the community members to put together more functions in different levels of implementation. We can implement them, or we can work with you to put your code into UXarray as well. I hope it was helpful. Again, apologies from my timing capabilities, so I'm not good with that. There were some additional links that we put into the tutorial outline. We believe they would be helpful for anyone who is interested in unstructured grid research. That's everything. There was a question. Could you also address capacities or plans for zonal statistics? Rather than plans, we are, I think, 90% with them. So there is going to be zonal conservative averaging functionality around the corner. So our colleague who is working on it is almost done with everything after several months of research and implementation. There is going to be non-conservative as well. And other than that, we have an open GitHub discussion forum, and where we ask for people's requests for function prioritization. So if you have anything in mind that you couldn't find in UXarray, go ahead and put them there. And again, we will be very happy to work for them. I think this is everything we wanted to tell you today. So they are going to be, yeah. Again, these subsetting and remapping and functions are for 99% visualization purposes. Because, if you can visualize, you can really get started with analyzing your data. So we kind of prioritized visualization over data analysis, to be honest. So any questions from the room or over Zoom? Was there a mention on data? Dask. Yeah, there was a mention on Dask. As we are inheriting from XArray, we should be 100% interoperable with Dask. And we have tried ZAR datasets, we have tried Dask clusters, and they seem to be working well with UXarray. But if you have any questions or feature requests or concerns, maybe some bug reports, please reach out to us. Any more questions from the room or Zoom? And at the same time, I would like to be respectful of people's break time, so I wouldn't like to go over a lot of things. Any more questions?
There was a question about converting structure, the best way of conversion to structured grids. So I assume going from unstructured to structured. It is useful for getting initial conditions for some models. Would you suggest remapping on a regular grid and writing to NetCDF or any other suggestions? So I can answer this one. One of our other interns, he's not here. He works, he's part of a partnership that we have with DOE. He's actually, him and I are working on getting native unstructured to structured remapping to be part of UXarray. Other than I would say probably like the ESMF package already has pretty well supported unstructured to structured support. but we
Yeah.
are looking to get that in as part of our native stack of functionality.
Yeah. There are still some questions, and I am more than happy to answer them, and I can keep answering. But at the same time, let's at least make an announcement. Like, I think we can finish it at this point. So, yeah, thanks a lot. Okay, and Philip seemed to have already answered that one. Yeah, thank you everyone for your time and patience. Thank you so much, Rachel. Philip, thank you very much. And now I think it's a good time for you to go ahead and have a good lunch for you.
Yep, thank you all.
Bye-bye, Philip.
And for anyone that's still in the room, I'll be available either via email, through GitHub. You can always reach out to me.
Yeah, Philip, really sorry about you having very little time for that part.
Oh, it's okay. I think we still got
Yeah.
through everything.
Yeah,
And
thank you.
we'll be
Have a good
sharing
rest of your day.
materials afterwards.
Yeah, absolutely. Yeah, bye-bye.
Okay. So welcome back, everyone. My name is Daniel Howard. I'll be presenting on GPU computing with OpenACC and MPAS Atmosphere. This will be more of a talk on the technical usage of OpenACC and such. There's a few use cases so far with the latest release of MPAS using OpenACC, which I'll highlight as much as I can, but nonetheless, this will be for those who are interested in engaging with furthering GPU development of the MPAS model, how to go about doing that. OpenACC has been decided as the primary choice for how the modeling team wants to move forward and porting it to GPUs. And there are significant benefits towards that goal. So I'll detail some of that in terms of what we offer here, at least the NCAR HPC facilities first. So before I go on, if you want to follow along the slides and you can feel free to scan the QR code, there'll be each break slide. For the just to highlight first, most of you will likely run this model on our derecho supercomputing system. It should be expected to try to be portable to other systems as well. But nonetheless, here's some details about our system that we have here. I'm part of the consulting services group team that helps support any users on our cluster. So if you are doing any work involving MPAS or really any other project, there are dedicated staff like myself here to facilitate your work and make your development and HPC efforts that much more smooth and easy to attack, so to speak. So the main GPU that's across derecho right now are the A100 GPUs. I will also note for the Casper cluster as well, which is more of a heterogeneous visualization and data analysis cluster that we offer as well. There are some actual H100 nodes for you to try out as well, not to the same extent of like 300 plus A100 GPUs on the derecho one, but if you wanted to play around with the other types of GPUs available, there are multiple types across both Casper and a few test nodes on derecho as well, actually with H100s. The one thing just to highlight in terms of why we're considering GPUs is that they enable exascale. If you want larger resolution models or running your models faster, be able to do more science, so to speak. Many of the top 500 supercomputers nowadays are in fact leveraging GPUs. Many of which are using NVIDIA, some of which are using also AMD. There's some even new ones that are exploring Intel GPUs as well. And one of the main things as well to emphasize with that is that GPUs enable more flops per watt efficiency. So that basically can mean lower running costs and easier access to big science. You can do more with less core hours, so to speak. And the main cost most data centers and research enterprises are incurring in terms of running these data centers is the actual energy input into those data centers, how much energy your models are using. So GPUs are inherently designed to be parallel. They are a graphics processing unit initially. They process each individual pixel or a set of pixels on the screen of your computer, megapixels worth of screen real estate, so to speak. Well, CPU cores, they're designed to be flexible. There are many different types of subcores within the CPUs to do different types of tasks. They're more flexible in that sense, but it's not as scalable in terms of the amount of work you can push onto a CPU versus a GPU. Nonetheless, there's some caveats in terms of how you program for each, and I'll go into that later in the talk. So in terms of just looking at the history of these NCAR systems, we have over the years, as we've added different types of processors and upgraded our hardware, achieved greater amounts of flops per watt, essentially, in terms of like for how much energy we're putting into the system, how much computational power we're getting. And so derecho is, of course, the largest one yet. We wouldn't want to make a new computer if we weren't getting an increase there. But a lot of that is coming from GPUs. So in order to actually achieve those this performance kind of metric there, you really need to be using GPUs in part of your models. Another aspect to highlight, at least why GPU is important, is that data is the future of scientific discovery. We're getting more and more data from either model outputs or as well as like remote sensing and satellite imagery that we would ideally like to process. But as we get like petabytes of this data, that gets really hard to sift through. But one of the benefits of GPUs is that they are capable of having a much higher bandwidth of memory that they can process over time. That's why they've also been really friendly towards machine learning models in the sense of how much data and like information they can ingest into that in a relatively fast time frame compared to like other types of hardware. So if in processing data that's increasing ever and ever more in the future is of concerns of yours, trying to figure out how to do that effectively in a GPU would be of value. Another aspect to highlight is that there are many other initiatives across the weather and climate forecasting space that are exploring and actively using GPUs, not just in like the AI machine learning space, but actually in the physics and simulation space. So here are some examples of like past projects that were highlighted by some collaborators from NVIDIA that work with these various teams. So just keeping that in mind in terms of say like other models you might be familiar with, and I imagine you might know maybe more than me actually in some ways how some of these models are meeting the cutting edge, so to speak, and the progress they're having on GPU enablement of their work. And for an MPAS case, at least back when we were focusing on the version 6 of the model, one of the biggest benefits, hopefully for you as a researcher and user of these models, is to actually be able to do more with like less time. So in some cases for this particular analysis, looking at running MPAS-A, that was GPUized for version 6 a few years back. When they compared that to the CPUized version of the same, they're actually able to get significant more days of simulation per hour runtime. So if you could think about that in the context, this is a logarithmic graph here. If you get like, approximately almost like 10 times more, simulation time for the amount of input you're putting into the model, think of all the different types of work you might be able to do, or maybe you might want to say go the other direction and get higher resolution models, go down to 5 or 3 kilometer resolution, but still have the same amount of like simulation time you're doing if you were just a CPU only model, but at 10 kilometers. So those types of improvements that we're hoping to enable as we're working towards improving the efficacy of GPU porting of models like MPAS. So why use GPUs in first place? I'm going to cover that just a little bit as I talked about it just now, but maybe go a little more details to why they are actually effective in this. So you can see here at least like a trend over time historically of performance metrics of various hardware types. The blue here is the basic CPU cores, and the red and green here in this black icons are the AMD, NVIDIA, and Intel GPUs over time. And you can see here that they do have significant more peak performance of like flops compared to their CPU counterparts. So, like the A100, which is on the derecho cluster, has about 9.7 teraflops of theoretical peak capacity there, whereas then the CPU that it's paired with only has about 3.6 teraflops. So, and that's just the compute part. But maybe something more stark to highlight is the actual like amount of data you can process. So if you're able to put more data or run more data on the GPU, that increase is actually much greater in terms of a GPU versus CPU. So we see the A100 here is 1.6 terabytes per second of data it can crunch through, whereas the AMD CPU that's on WHO has only about 200 gigabytes per second. So that's already like an 8 times increased amount of data. You can, if you do this efficiently and you program it well, that's what you theoretically would be able to achieve. Recalling back to that graph highlighted earlier amount of data, we basically having that higher throughput bandwidth capacity of GPUs can enable tackling this problem like this. For example, how you might go about doing that, that's up for you to decide. But nonetheless, it's a aspect to consider about like the value add GPUs are adding here. And the reason why the data movement is something of concern here, at least think about that, of how much data we can process. If you're able to keep the data on the GPU, you can like move between the memory store on the GPU at about a rate of like 1.6 gigabytes per second, as it just said, 1.6 terabytes. However, if I try to look at just the movement of data between the CPU and its memory, like the DRAM chips on a typical compute node, that gets around 150 gigabytes per second. So that's a significant loss of value in terms of what's achievable in this. Nonetheless, another aspect to highlight is which I'll get into more depth later, is the data management piece of like there's a totally different programming paradigm that you have to navigate when you're designing software for GPUs. Most of the time, when you're developing, which you might be used to right now, you're obviously developing work on a CPU predominantly, and you're then using only this memory space. But when you start adding a GPU, you have to manage the memory that's distinct between the CPU side and the GPU side. The unfortunate part is that the speed at which you can move memory between each of these sides is very small. That's why this line is very thin. It's a PCIe bus typically to move memory between the CPU and GPU, and that's about 32 gigabytes per second. So it's a much slower amount of speed of memory movement. So and highlighting that, we'll talk about this a little bit more later. You want to make sure that whatever data we're processing on the GPU stays on the GPU and minimizes the amount of movement back and forth from the CPU and GPU. And speaking about energy efficiency, I mentioned earlier, from a historical context as well, we were gradually over time, like say, shrinking transistors and adding more transistors to chips. But as that has played out, and especially around the early 2010s, we started to approach the heat dissipation limit of how much heat we can actually pull out these chips without it melting too fast. So we were able to quickly over that period of time, we might be familiar with Moore's law, able to achieve a significant amount of increase in performance. But now we can't really expect too much performance improvement with each generation of new hardware type, just because we can't really make transistors that much smaller. That we're reaching this heat dissipation limit. We're starting to level out here in terms of able to manage that heat load. So in order to given that the past decade and a half has been more focused on incentivizing use of parallel processors more effectively, and GPUs as a hardware type in and of itself is parallel beyond just parallel in the sense of MPI across different nodes. So you can't expect a free lunch anymore in terms of like your next iteration cycle providing you a better computer and thus automatically improving your performance significantly. There really has to be a lot more work towards how you're designing the parallel implementation to do that effectively. So in terms of like why we decided on GPUs in the first place, there's some comparisons done in the past in terms of going towards what future we might see. And this purple graph ended up having the greatest efficiency. This is energy per flop, and so in terms of this prediction here, and so these heterogeneous type scaled nodes were the ones that were chosen as like the path forward likely in terms of like a CPU plus an accelerator GPU type card. The other competitive one, which is more like the Riken Fugaku supercomputer, which have simpler RISC-V type processors, or sorry, not RISC-V. I think they are processors. These are these green circles down here are more lightweight type CPU rather than the heavyweight ones like the Intel or AMD ones you might be familiar with that are x86 based. So basically, it's either learn how to in order to get the greatest efficiency here, we have to be able to use these heterogeneous platforms most effectively. And the reason why the GPUs are in fact more efficient is that the physical design of those hardware types typically have the memory that much closer to the computation. So if you look at just like the amount of energy use based off the distance the electrons have to travel within the hardware, if you have to go to like, a DRAM or off chip somewhere, you're often spending, like orders of magnitude more of joules in order to do that, say a 64-bit operation. But if you're keeping that memory within the chip or nearby, it is much further reduced. And so, and GPUs are designed inherently to accommodate that type of data movement pattern. And so, if you're interested in reducing the carbon footprint of your model, to keep data moving nearby, you want to make sure you're not moving data too far, not too often, and in so doing, you can minimize the amount of energy you're spending within each time step, for example. So as a study to like highlight that, Richard Loff had back in 2020 had given a talk about reducing the footprint of MPAS weather modeling with GPUs, and just made the note that like at the time with comparing the CPU-ized version of MPAS on Cheyenne and the GPU one running on Summit, you get about a 4x improvement in terms of or decrease in kilograms of carbon emissions for a 10-kilometer global one versus then a similar scale magnitude of improvement for a 3-kilometer one. So I don't know how often you think about that, and each time you submit a job in these clusters, how much like energy that's using, but it's often a lot. So there's a value add here in terms of thinking about that these types of work towards meeting the efficiency needs of the types of hardware we're running at, and prioritizing that work beyond just the science in of itself. So there's definitely a value to incorporate more software engineering skills and researching colleagues that might be had the expertise within your teams, and make sure you're integrating those folks to inform best practices of how to do that meaningfully. So as a last thing, just like something to highlight over time, like at least as new generations of GPUs are coming out, there has been a trend of increasing flops per watt efficiency. One of maybe the unfortunate side effects of that as well is that there's just more energy being pumped onto a GPU. So I think the next Grace and Blackwell Hopper GPUs will be have 750 watts and 1,000 watt usage of energy for each chip. Whereas I think the current one uses like 600 to 800 watts. So each chip is using a lot more energy, but nonetheless, you're just getting a lot more flops per energy input. It makes some of the system engineers' lives a little more harder in terms of managing the energy dissipation, but nonetheless, it is a value add in terms of if you are actually using those GPUs effectively, and you can at least expect a greater efficiency in that power usage over time, if not also a performance improvement. One other maybe aspect to highlight is that GPUs are very adaptable and flexible, and actually prefer different precision types of the input data. So double precision, of course, works with typically for the ones that we provide. But if you are able to run in single precision or even half precision, I imagine single precision is probably preferred. But nonetheless, that you already get doubling the throughput. That's already 64-bit to 32 bits worth of memory for each variable you're pumping through, and that's just that much more data essentially you can fit on the GPU and thus then pump through at the same time. So there's significant opportunity cost if you're going to use double precision, and thus then I'd encourage you maybe to evaluate if you actually need the double precision or not. So just to get some primer ideas first out there about how we design processing and parallelization on GPUs. We should talk a little bit about vector and thread processing. Any questions so far from the earlier portion? Yeah.
Hey, just a quick question. How is the internet connections in these GPU hybrid machines? Is it InfiniBand, or I assume you cannot cram everything onto a single compute node?
Right. So like each GPU, at least on derecho, has 40 gigabytes of memory. There are other systems that have 80 gigabytes memory. And within that chip hardware piece, there's what's called a high bandwidth memory connection between its memory that's slotted to it and like the compute components. In terms of mentioning InfiniBand is more for a cross node communication. Right. So in like the Rachel is currently using a newer implementation called Slingshot using libfabric. That introduces some complexities that hopefully you don't have to deal with too often. But if you notice any issues there, like I'd encourage you to reach out to my team as well. We do often troubleshoot issues with libfabric and Slingshot.
No, I'm not with NOAA or NCAR, but I'm be interested in, well, I assume that I will need at some time in the near future to up my HPC to a GPU-based system.
Yeah, and like I think most HPC centers will have their own support staff, but I think the NCAR teams here as well would want to make sure that our models are relatively portable to other systems. So we'd like to know where they're failing and what might be a reason for that, if that's something we can address as well. So encourage you to just engage with any of your colleagues here as well, like in terms of like, how to report that most effectively. So, given that, I think I'll move on. So this is a brief, summarization of just some basic computer science concepts. As Flint's taxonomy here is basically a way in which we can think about how we process data. You either have like a single instruction operating on a single data that's typically like one CPU thread. The most common one you often see is a single instruction applied to many data at the same time. So you have like, many different cells in like, your MPAS model, and each one has the same types of operations acting on them. Or maybe you're working in a vertical column, and like each cell within that column has to have the same operation applied to it. That would be a typical type vector processing. They're often done either as SIMD on a CPU, or in the GPU context, they actually change the name to SIMT, where T is now threads. So, but they're essentially similar concepts in terms of like the parallelization that's happening. There's other kinds of like multiple instruction, single data that's not typically encountered, and then also multiple instruction, multi-data, and that's typically for MPI type communications and doing different operations across nodes in different memory spaces. So one thing at least to highlight and reiterate again in terms of like the performance difference between CPUs and GPUs. Here we have a CPU AMD EPYC bus. It's very red for AMD, and then we have at least the grass is green here with the Shinkansen, the train. I'm kind of a nerd about public transit and transportation issues. You get more efficiency if we had a train. But part of the thing is like you think about, say, with a bus, you have like 64 seats. Maybe you have opportunity to have like 2 cups of like drinks in your seats or whatever. It doesn't perfectly apply here, but nonetheless, you get about 512 SIMD ops on a bus. Whereas like for the number of SMs or the processing units within a GPU, each SM can then have 64 warps for it. So think of that like, each SM is like a train car, and then you have seats in that car. And then each person can manage 32 SIMT threads per that seat. You're getting like about 200,000 operations per like that you can potentially parallelize at the same time with a GPU compared to the 500 for a CPU. So you can, and think about the same in a real life context. The busiest bus terminal in the world is New York City, and that's like about 200,000 people per day. Whereas Shinjuku, Tokyo is upwards of 3 million people per day in terms of how many people it can process. And that, the downside, at least comparing the two, is that like, a bus, you're on a road, you're much more flexible where you can go. There's different types of, there's complex ALUs, algorithmic logic units on a CPU, so you can navigate different tasks much more easily. Branch prediction is offered on CPUs to manage how you're navigating if-else type statements effectively and not like leaving threads idle. But with the GPU, and once you get going, you're doing pretty well. But you're confined to that track you're on. If you then like need to move some other places, if it has to like branch someplace differently, there's no branch prediction options available on GPUs, and so if-else type operations are often discouraged on GPUs. If you end up doing that, you end up leaving like half the threads or more idle as it waits for one side of the operations to work. And then if you have to move data, so you passenger load or deload, every time you stop at a station, that's a significant cost. So you want to minimize the amount of times you have to move people or move data on and off the GPU. And as I mentioned about branchless programming and branch prediction, if you do want to, if you absolutely need if-else statements, there are like design patterns to get away from that. So you can do, this is an example of like how to do a branch list implementation of a if statement. So that's just a fun way of like a programming trick to get around that, but I won't go into that too much detail. Nonetheless, awareness of threaded processing will help towards optimizing the performance of GPU kernels or your compute units. So, hopefully, this is a brief introduction here if you're not familiar with the types of design patterns of how threading works on these types of processors. But I encourage you to learn more as you say, and dive deeper into engaging with this work, or at least like have some more terminology behind your belt as you might work with other research software engineers to support the implementation of any new microphysics or other types of schemes you might be working on adding to MPAS or implementing. Now we're going to get towards the actual like software paradigm of like using OpenACC, for example, and different approaches we have towards building GPU software. So one thing I'll at least emphasize first is we want to make sure you want to think about, say, who are you trusting in terms of the tool chain that you're using even today versus even then when you're using GPUs, of how all your software is being built. Most of us, we're at least minimally familiar with, like, we can run the compile command, maybe a make command or some sort of script that's available to us to build our software once we receive it from a GitHub or wherever we might get it from. Nonetheless, there are many lower levels of computer architecture that we don't directly interact with, and many times require little awareness of, and I would actually expect you should not have a lot of awareness of. The goal is to, we don't necessarily want you being worrying about like, logic gates within the microprocessor and how to navigate that effectively. That's what a, microarchitecture engineer type of person should be dealing with. You're just dealing with the software. So in thinking about that, are you willing to actually place trust in the person who's providing you that compiler, that's the system you're working on, to build the software as you intend? It takes that like willingness to be part of that co-design process with your colleagues and peers that provide you these tools to make sure that we're meeting each other where we're most effective. So and thinking about that in terms of what type of software stacks are provided, like there are different compilers and such, and since Derecho's a NVIDIA-based GPU system, NVIDIA does have their own software stacks for providing development on their hardware. So obviously they support working with standard C and Fortran codes, but they also support OpenACC and OpenMP, which you might be familiar with as well. And then CUDA is the more lower level implementation of how to interface with the GPU. They also provide their own compilers and things, but most of you here will probably just focus on how am I developing this programming model within C and or Fortran, and then maybe using OpenACC. And if you want higher performance, you might add these things, but you're not necessarily going to these other sides perhaps and like fiddling with the compiler too much. You're not going to like recompile a compiler to build your software again. If you do encounter those issues, you reach out to those compiler teams and they fix it for you. So part of it is just recognizing that there's been a lot of efforts on these like other tool chains to make your life easier, and I'd encourage you to use that to your greatest benefit. It's not expected of you to get into the weeds of these other tools unless you so want to. Maybe the most you might use are like the libraries, for example, here, but you'd be a user of those libraries, not necessarily someone that's like adding to the libraries too much. But it's important to at least be familiar with what's meant for you to access and leverage as part of the tools available to you already within a software ecosystem, rather than always trying to reinvent the wheel. There's probably someone else out there that's already done something to make your life easier, and I'd encourage you to find those tools and add them to your toolbox rather than reinventing a new tool every time you say want to multiply matrix together. There's specific libraries, for example, that do that and do that very much more efficiently, say with like the BLAS and cuBLAS libraries. In mentioning that, OpenACC and directive-based programming, they often focus on what's called descriptive versus prescriptive programming. So, in the way that they're implemented, you often add comments to a code, and let's say around a parallelizable region. And they can either be very explicit in terms of like how you as a programmer want that region to be parallelized, or it could just be like, this region is parallelizable, compiler, please do what you think is best to do that parallelization for me. And so OpenMP traditionally has started off being much more prescriptive in terms of like, you need to specify how many threads you want to distribute on the CPU and which way, or like, and like how they might be avoiding locking with each other. You know, MPI and CUDA are much more like, you have to be very, very detailed in how exactly those libraries work. Whereas descriptive context, OpenACC started more focusing on that side, and there's newer actually ideas that are inherent in the languages themselves, like do concurrent or std_par. This is in Fortran, where it's actually part of the language standard, and std_par is part of the language standard of C++. Whereas all you might have to do is just say, you know, you give guidance to the compiler that region is parallelizable, and then that the compiler engineer is someone that has thought about the various ways most loops should be parallelized and should do that in an efficient way for you, so you don't necessarily have to go into the prescriptive, more difficult task of figuring out how to do that in CUDA. Mentioning that's why I was valuing the you know, what do you trust your other colleagues down the line in terms of like the tool chains you're using? Do you think they're capable of if you say give them a hint at a specific part of your code that this section should be put on the GPU, do you trust that that compiler person that developed that process can do that effectively, or more effectively than you, or less effectively than you? It's that's a valuation decision I think for you to have. You know, like certainly if you're an excellent CUDA programmer, maybe you should do that. But nonetheless, you know, I imagine most folks, you want the easiest on-ramp as possible, and OpenACC is one of those because it focuses on this kind of more descriptive pattern, and it offloads the harder task of how to actually do that GPU parallelization to someone else within, say, the compiling team. Just to compare some of the types of GPU programming options available, you know, say if you want to, you know, make C or Fortran like GPUized, you might say add some CUDA code, or you can use OpenCL or Silk. It's more of an Intel implementation. OpenACC and OpenMP are very similar to each other, so within the same box. And then HIP is the AMD version of CUDA. If you want to do the very low level CUDA or HIP, you often require new code and VWrites. It's a much more intensive process. It takes a lot more of your time as a developer, and maybe time away from your research or other tasks you may have to do. So you know, unless you're very proficient at that work, you know, that you should evaluate how much effort is actually required to do that type of GPUization of a code. Whereas for like OpenACC or OpenMP, those are all pragma-based. You're just adding comments, and depending if you add the flag in the compiler or not, they can be ignored. But they're often easier to implement. You find a for loop, you add like a line or two of comments around it, and then you already get a GPU-wise version. Whereas if you try to do that in kernel, you probably are adding like 10 to 20 lines for each GPU kernel. So thinking about like that sort of comparison's sake, it allows you to like evaluate, hey, I can probably get this on GPU much more quickly. And down the line, if you find out that like one kernel is like very important to the performance of your model, say you have to profiling it, you can maybe, you know, individually, you know, optimize that kernel with a lower level CUDA implementation, or whatever way you might, you know, approach to do that. So if you do need the best performance for a specific GPU kernel, you can use CUDA or HIP alongside the OpenACC or OpenMP type GPU offload models. So just as a best practice with GPU software for development, you know, there's an order of operations here in terms of like what should be applied. So you know, if you have a standard type of operation, say like a matrix operation or some sparse matrix operations you might be doing, there already exist libraries that do that for you, and you don't necessarily even have to like think about which kernel goes where, and just, you know, you can just drop in that library. So you should do that first. That's already someone else has built out these very efficient libraries, and if that is an opportunity available to you, like do that. Then you know, if as you just wanted to be on the GPU and just actually, you know, get your project going, you know, I probably just go with, you know, adding some directives and doing that iteratively towards getting good enough performance. Typically, the ways in which compilers offload the GPU code, it gets you, you know, satisfactory results in like how well the code does. But if there's a few sections of the code or specific like costly kernels that take up a lot of the time, you might say look at those specific ones and then add CUDA programming or some sort of lower level approach to optimize that further. Keep in mind though that last one again is the most effort. So highlighting here is just there's this order here in terms of like what is most valuable in terms of like adding first, and also in the sense what's easiest to do. You don't necessarily want to spend 10 hours doing CUDA for everything when you could do most of it in 1 hour with OpenACC. And maybe if you have one kernel that needs to be much more highly performant, then you spend 1 hour on that one kernel. So it's kind of like we all have limited time, including software engineers, and you yourself maybe as a part-time software engineer, and evaluating what is most effective and biggest bang for your buck is valuable in that space. So when using all these approaches as an added point, it's also important to measure progress. So you typically want to use a profiler, determine a limiting kind of function or space in the code that's slowing you down. And then once you find that, you assess it, apply some optimizations, and like iterate that over and over. So there are tools like Lenora Forge Map, and I saw that within MPAS there are actually some tile integrations already. So you can use those as profilers, as well as then the NVIDIA provided profilers, including Insight Systems and Insight Compute. So just like as a performance comparing performance of programming paradigms, OpenMP and the standard language parallels approaches like StudPar and OpenACC, and those all are relatively similar to each other. That depending on the kernel, they can one can be better than the other, but like there's not that much difference between most of them in many cases. You can experiment with that as much time as you may allow, but in highlighting that library case, if you do have kernels that are able to leverage, say, cuTensor or some other like performant library in their code, those are often much more performant than like trying to do any of that optimization manually. So it's just highlighting here again that like those libraries, the optimized libraries are very much the first line of defense, and like what you should be adding as you can identify it, and then further down the line trying to any of the other choices are relatively similar to each other. Nonetheless, OpenACC is what I'll be focusing on today, but there are ongoing discussions within the RSC community in terms of like which paradigm might win out. And it's a hard discussion to have with a lot of people I know I regularly talk with. In any case, just thinking about also future directions of GPU programming. Obviously, we don't want to like buy into a model or paradigm that might die out within 10 years or 5 years, but before the end of a project. So nonetheless, tools are constantly being expanded upon towards increasing performance of these descriptive programming approaches. The issue, at least between OpenACC and OpenMP, is that they are both well established now, but they kind of compete with each other. And the different compiler teams that make those compilers, they don't necessarily want to support two standards at the same time. So how they will continue to compete or not compete, maybe even merge on the line, that's an ongoing question. But there is within the OpenACC community, the Open Accelerating Computing Consortium, more interest now in the standard parallelism approach, such as do concurrent and StudPar, where that is more inherent in language itself and not reliant on comments and directives. So I personally anticipate that probably taking off more so in the future. But the way in which those are supported currently do not allow as much flexibility with, say, managing data movement, which you will likely need for current implementations using OpenACC and or OpenMP. So nonetheless, there's the overall goal that we want to promote portability in any software design pattern we choose. And there will always be more and more people developing robust libraries, improving on those the same to make sure that those are adapted to current and future hardware releases as they come out. So you might be familiar with like MKL and like CPU, the math kernel library that Intel primarily maintains, but NVIDIA had their own GPU equivalents, and AMD has their equivalents the same through the AOCC, I believe is their like acronym for their like kind of like library collection. So feel free to explore those types of libraries there as they are continued to be added upon and improved. So any questions from that section briefly? Oh, yep.
From online. can GPUs access the same amount of memory as CPUs currently?
So in most cases, no. So I believe our derecho nodes, for example, I think have the CPU side of memory is 512 gigabytes for the GPU nodes. I may be mistaken, it might be 512 or 256, but nonetheless, the GPU only has 40 gigabytes. So you know how much memory model where's the memory you can put on the GPU, you have to manage that accordingly. And there are ways to actually concurrently move memory at the same time as you're processing compute on the GPU. So as you're waiting for some section of your model to like compute through, you can be offloading and uploading memory as needed for the next compute phase. And thinking about that is part of the process of designing an effective GPU program. Is it, any other questions? I haven't looked through the chat briefly. I see I have built HDF5, NetCDFC, NetCF4Tran, MPitch, and PIO on my Windows subsystem for Linux, and I'm attempting to run MPAS, which is GPU enabled on Windows subsystem for Linux. Have you tested MPAS in WSL, or do you have any suggestions regarding its setup? Yeah, and I think there was actually answered in a comment there. I don't think we have not. I don't think there's much. I mean, like it is a Linux subsystem, but there's probably not a priority there to manage that particular feature. And I don't expect even my own group that would be our own priority. We would this consulting services group, for example, primarily supports what's under our supercomputing infrastructure. And I don't believe WSL is a common feature even in other HPC centers. So, but you're more than welcome to start like forum threads and interactions with other community if that is a priority for your needs. Okay, I think that's all the questions on the chat. So I'm going to close that and move on. So here's some like historical cases of like navigating GPUization of and manufacturing various projects. So this is one with Lawrence Littleton National Lab and Sierra and El Capitan at the time. The interesting aspect maybe here they'll highlight, and it doesn't perhaps perfectly apply here because they often will use like Raja or Cocos and some of the DOE kind of labs, which is another kind of type of programming paradigm for GPUs. It can take a long time, but like there is a typical like path forward in terms of how to go about these types of projects. So one way for, just there's some 7 points here that they highlighted here in terms of part of that presentation. You want to like basically refactor and remove any GPU anti-patterns. So that's like thinking about like how to reduce excessive memory movements. Global variables don't definitely work well because just the memory is distinct between the CPU and GPU. Certain types of data constructs or classes, those can be incompatible as well. So you have to figure out if you have any of those that exist in the current CPU-based code, you have to figure out how to like redesign that. And also just like to help make, say, if you have a very large code, how to even approach that large project. It's often important to say, do that in like smaller steps. So maybe making a mini app first to explore the design space. And then using portable abstractions and frameworks. So that can be in the DOE's case, it was Raja. But for us, we're leveraging OpenACC. If we're expecting everyone to like redesign the millions of lines of code at MPAS with CUDA, that's a lot of extra work compared to something that already encapsulates some of the underlying expansions that essentially OpenACC does in a much more compact manner. And in a sense, it's also allows some portability. OpenACC and OpenAP, their goal as organizations is to also make sure that their programming paradigms are compatible across different hardware types. There's different like kind of steps here they recommend as well. But nonetheless, like even though this timeline for their project looks like a really long time, and it probably will be for any climate weather scale type model, nonetheless, these best practices are now relatively well known, and thus then I would anticipate that so long as you plan for and engage with research software engineers early on in the process in terms of how to approach this problem effectively, you can probably shorten these durations in terms of like the amount of development effort required for some of these types of projects. So feel free to use the knowledge and tools that exist already out there. in terms of like how to maybe engage the way in which you want to make MPAS more GPU enabled. Okay. So another point to point out is that for during the course of most GPU projects, the initial porting efforts will actually end up making your model slower. Don't be discouraged. That part of that is that data movement part. So if you're not dealing with the data movement up front, you can often say you compile and run your first GPU model, you might get 100th of the performance. That's like this example here that they had. But as you say, manage that data movement, get rid of GPU anti-patterns, add some queuing structure and managing asynchronous execution and pipelining. You can then get the performance out there, but it takes that work to figure out how to optimize it. And it's not necessarily a trivial process that you can, just because you want it to be on GPU and it's you know that GPUs tend to be more effective, you have to do the self-engineering like effectively to actually get that performance you want out of it. So just, in saying that, don't be discouraged, but just like understand that there's a process involved to get to the performance you might be wanting to achieve. Overall, as I said, planning and awareness of tools available is important to getting you the most benefit. Adoption of RSC best practices and engaging with those colleagues that have expertise in that space and coding them, adding them amongst your team, making sure that those software engineers are actually participating in your group meetings at the same time and not just off to the side somewhere doing the software as if they don't do the science. They should all be integrated well with any of your work, and they have important contributions to add in terms of making sure that these efforts proceed effectively. So that essentially summarizes like the benefits and why we're pursuing GPUs in the first place. Any questions? And if you reference the slides later, these are all links you can click, or you're welcome to Google those titles as well if you so like. So now we'll get more to actually using OpenACC and some specific examples as it has been already implemented in some sections of MPAS. So I know it's a very wordy slide here, but just some useful definitions. Hopefully you might be familiar with some of these, but I'll go through like the first 5 here, but I'll probably explain the others as we go along. The device typically refers to the accelerator, as in your GPU. The host typically is your CPU. That's what's managing and sending out the work to the GPU typically. Hence it's called the host. It's kind of like the management of the operation. When I typically refer to a kernel, that is the computational set of code that's actually running and doing the compute work on the GPU. They're often scheduled in a sense to run and compute CUDA streams on GPUs. So, and depending on how you schedule that, they can either run sequentially or they have to like have startup and exit costs for each of them. So that's something to think about as I discuss kernels. The execution stream, that's the stream itself is where what the kernel is being placed upon. And so it's typically then that sequence of kernels to be executed on an accelerator. If they're allowed to be synchronous, then they can run right after each other. If they're not asynchronous, then you often have to wait between each stream finishing before the next one can start up. And then a thread is a single processing element or execution unit within a kernel on a stream. So as I mentioned, like a GPU can have the opportunity for about 200,000 plus threads running at the same time, whereas like a CPU have only 500 amount of threads running at the same time. So basically, that's when we define the amount of like work assignable to each kernel we might be launching, they'll often be discussed in like number of threads being distributed across within a kernel. And they'll often be distributed specifically on the streaming multiprocessors, the SMs, but you don't necessarily have to think about that too often. But there are some details there. You can maybe go into further in the weeds if you so like down the line. So I mentioned earlier that OpenACC and OpenMP are relatives. So when OpenMP was in its earliest phases, or one of its more matured opportunities in this third iteration, I believe OpenMP was more hesitant towards providing a GPU offload capability. So then OpenACC was born to meet that gap. It ended up doing that successfully over a few iterations of releases. And then OpenMP finally added its own version of GPU offload in version 4. Nonetheless, like OpenMP is predominantly managed and maintained by the Intel community, whereas OpenACC is managed by the NVIDIA community. Whether or not those would ever merge in the future, I don't really know. And it's a little bit of a political mess between the two of them, but nonetheless, it offers some interesting case studies between the two in terms of the different ways that each approach GPU offload capabilities. Just getting to OpenACC. OpenACC, as a acronym right there, stands for the directive-based programming paradigm, which uses special comments in existing code to offload computations to accelerated devices such as GPUs. So if you look at the right here, you have like a typical, your program, my science, you get some serial code, and then you get to some do loops. The do loops is something that can be parallelized so long as everything is independent from each other. There's no dependencies between the loops. And all you'd have to do with the OpenACC implementation is to add these comment typed sections that have these special formatting, and Fortran has this exclamation $ACC that signifies it's an OpenACC comment. And in so doing, when you run the compiler against this now code with added directives, it now knows to port that section of the code, the parallel code, to actually run on the GPU instead. So typically the way that works, and it's similar to OpenMP, is it's a fork join execution model. You have your initial serial thread before your parallel loop. It gets to this fork in the road, and then it distributes a team of threads to run that parallel code. And when it finishes the parallel section, it then joins back those threads and continues on with the program. So that's like one way to do that in terms of thinking about how this like model works as a framework. One thing to briefly mention is the OpenACC community is now, given that the standard is much more mature, they're actually focusing more on supporting the community effectively and optimizing and porting people's codes. And so they like regular hackathon events you can join and learn about how to do. They're often teaming you up with various NVIDIA folks or other professional experts in the field, computational scientists at national labs and other folks to support your work. And so in so doing, they actually now call their acronym the Open Accelerated Computing Consortium, towards that goal of offering a community of folks that are interested in furthering the performance of scientific software. So again, what is GPU offload? The key part here is, remember before, most of the code is initially running the CPU, but at some point it has to move onto the GPU. So when you get to that GPU offload portion where that fork join happens, you have to send the data over here to the GPU side through the IO bus. And where in so doing, when the GPU offload is happening, that is where the computation is then offloaded from the CPU to the GPU device. Additional steps are often necessary when that happens. As I mentioned, it has to move that data. And so, it's very important to consider the data movement, and just repeating this multiple times, given that slow bandwidth between the host and device. And, if every time step you have to move data between the GPU and the CPU, you have to wait every time that happens. And, if there's any way you can avoid that, or maybe only move scalars and not full matrices or something like that, that's of a significant value towards making sure your code runs efficiently and smoothly. So just to highlight some basic directives and syntax within the OpenACC paradigm. Again, it uses compiler directives for defining compute kernels and data transfers. So the important constructs to consider, there's execution and data constructs typically, that they often will have the parallel is like the basic kind of like, this is a parallel region, and then kernels construct is one that specifies that this region is then more of a descriptive here. Like this one is parallelizable. Please do what you want with it. Whereas if you had the loop one, that's more of a prescriptive one where you're allowed more flexibility and control over how it's parallelized. The wait construct here, you can basically just tell the streams or runtime kernels to wait until they all finish. And the async one is actually a clause that can add any of these to make sure that kernel that's being executed is run asynchronously. The async one can actually also be added to the data one. And really, I should have put it in this clauses down here. But in any case, the data one are different directives as well that just suggest that this is a data movement type operation that's taking place where that comment is placed or the directive is placed. So you can start a data region, either you can enter and exit a data region. You can also update data by force, so to speak, by specifying an update code. So you want to, let's say at the 100th time step, you want to write out the state of your model. You You can then update the matrices or data variables that you need to like be on the CPU before it saves it to a file somewhere. And that would often be that command you'd use in order to do that. And then host data is basically just like, signifying this data already exists on the host somewhere. But we won't go into too much details into that one, as that's more of a special use case. There are other clauses. You can say like, do a certain clause or operation if a certain condition is met. These gain worker vector clauses are just specifying the way in which work is distributed and the tasks are distributed within the kernel. And then the copy, delete, create, those are part of the data type movements where, say, if you want to copy data, this one copies in and out at the end of each copy region. But there's also a associated copy in and then copy out clause as well. Delete deletes data, as you mentioned, and creates data, just allocates, but doesn't have to move any data. If you want a complete listing of like all the different directives and their syntax and how they're used, there's a quick reference guide here that I encourage people to review as you get more familiar with OpenACC. So here's just a brief little chart of the most important ones you might be need to be familiar with. So if you're in C, here's a syntax in C++ for how that's used. You have a hashtag instead of exclamation dollar sign for how these are initiated. And again, like we have these execution model type directives, and then we have data model type directives. And they often are distinct from each other. They don't typically mix, but they'll often be near each other. So we'll show some examples later of how they're used. But just to recall again, some of these directives are more prescriptive and descriptive, as I mentioned. So the kernel's directive is more descriptive, describes the loop being parallelizable, and the parallel one offers you the opportunity to add additional clauses to it, where it can be prescriptive of how it's parallelized. And depending on the type of performance or amount of work you want to put into parallelizing a section of code, you can either choose either approach. And one way to even do it is to often just do the kernel's descriptive approach first and just see how it performs, and then iterate from there to like add more prescriptive configurations and specifications of how each kernel should be run more efficiently. So using like the descriptive approach, with the kernels clause, you'd often define a region to be offloaded as a sequence of kernels for execution on the GPU. So that and with the descriptive case, as I said, the compiler is given freedom of how to do this. So when you add this, you just basically surround a for loop with the ACC kernels directive here, and you add any additional clauses that might be relevant. Same thing for C. If you specify additional like loop nests inside the region, they'll be separated into separate parallel kernels, and each separate kernel containing parallel threads will be executed in sequential order. So if you're in a kernel's region and then you have like multiple sets of for loops that distinguish from each other, but each have like a loop specifier for each, they'll still happen in a sequence unless you add the async clause that puts them in different streams. But nonetheless, it's that's a standard operation if you just only include this kernel's operation and any loops within that region as well. And you don't necessarily even need to add a specification for loops within the region, as the compiler will do that for you. It's basically just a one-line fix it, but it just doesn't offer you a lot of flexibility. And sometimes the compiler can do it poorly or even wrong on how it parallelizes. It's up to you as a programmer to make sure that the region you're describing as parallelizable is in fact parallelizable for it to work effectively. In a prescriptive case, you use instead the parallel construct, and then you'd also specify loop for specifying work sharing constructs. Without any work sharing constructs, the whole region is executed redundantly multiple times. So given a sequence of loop nests, each loop nest may be executed simultaneously. So you want to be more careful in using the parallel one in terms of like making sure you're accurately describing each loop that you want to be running in a parallel fashion or not. So there's some additional clauses to think about. I'll focus on some three here. Collapse here is important. This one basically, if you have multiple tightly nested loops, you can collapse them all into one like large loop. You can unroll the loops, as it's called. And it's best utilized when you're Innermost loop is not a optimal size for vector work. So vector work is often of the order of 32 or 32 multiples of 32 units of work at a time. That's like amount of threads exist in each gang of work that is just how it's scheduled on the GPU. So long as if it's not an optimal size, you often want to collapse it, so you actually like expand the amount of work to distribute more effectively across these task granularities that the OpenACC compiler will do for you. Another one that's important is reduction. So if you have to say apply a sum or product sum or max min, etc. type operations, then you need to specify that variable is being, say, summed into. Otherwise, you can have like race conditions happening where data can override each other as you say summing into the same variable. And so this basically just does that, forcing the compiler to the runtime to wait between each time it's like say updating or adding into a variable, such that it does an atomic operation inside. You can also just do the atomic operation manually yourself, but I find it often easier just to do the reduction as it makes more sense to me. And the last one that's often important is a private clause. So if you have say a temp variable or something like that that's needs to be private to each thread or operation, then you would want to specify that those variables are private to each parallelized work unit. So otherwise, again, you can have like data overriding each other, and that's not good. So just as like a basic example of like showing this in like a easy sense here for if we have a doubly nested loop going from I to J of size n and m, say you want to sum the total kinetic energy into the sum variable. First we can, if you want to be explicit about it, we probably could actually do since this is such a simple example, we could do ACC kernel here, and it would just do that relatively fine. It's a very simple example. But if there's any complexities in this dot here, just ellipses here of like other code that I'm hiding, that might not work so well. But so in that case, having this like parallel loop and collapse, you can collapse 2 for the 2 nested loops you have here. And you can specify you're doing a sum reduction into the sum variable here. So this is a type of example of using these directives in a simple case. So I was mentioning task granularity a little bit, gang workers and vectors. And so, gangs are collections of workers that each have its own assigned cache to them. And then each worker has multiple sets of vectors of operations. So, typically each of these vectors will be of size 32 or even up to like 128, 256. You can specify the size of those vectors. But it's depending on the size of each of these work units, they get distributed differently across the streaming multiprocessors on the GPU, and you can play around with the ways in which these tasks are distributed to improve performance. But oftentimes 32 or 128 at the vector level size is often gives you your best bang for your buck, and you can experiment with that further in terms of figuring what does best. And the compiler itself will even try out its own what it thinks is useful. But if you want to further optimize or improve performance, it can be helpful to explore these different ways it's implemented. And so basically, you would add, you say you have an ACC parallel loop region. You can add a gang worker vector clause to it to distribute work and gangs of type gang or worker type or vector type. There's even additional clauses similar to these in terms of like gang size or vector length to specify the actual like size of amount of these types of tasks. So these are just different ways to manage that. And as one thing, just to like mention briefly, I talked about the wait clause earlier. You can add a wait clause to any of these in order to like say a previous kernel is running and doing some operation, but that next kernel is dependent on data being fully computed and finished before the next one starts to run. And so you can basically add a wait directive as well as any of these other ones to this comment here, such that it'll wait before that stream completes, or if you don't specify a stream, it'll wait before all streams complete before actually starting the execution. So there are different ways and ways in which you can explore advanced methods to improve performance and explore ways in which OpenACC can accommodate that. So, there are these are some of the most useful ones, but you may or may not have to use these as much, but it's something to at least be aware of as you, especially as you see the output for the compiler itself that will specify, hey, I turned this loop into a gang or a worker or a vector, even if you didn't use that clause, because it'll do that automatically for you, whether or not you use these specifications or not. So here's a specific example that's actually used at line 3246 in the version 8.2.0 release of MPAS. So say we have this parallel region that we're starting up. We add this wait clause. We want to make sure that the previous work that had been doing is actually all finished before starting this next set of work. And so now we have this first cell that we're going set of cells we're going to work on. And we're going to set that as a section of loop work. We're saying within this parallel region, this is now a parallelizable loop that we actually want to parallelize. And we want to say that there's gangs, and this is a gang and worker type level of parallelism that we want to apply to this loop body. Additionally, we're mentioning that these two variables here, the scalar tn column and wdtn are privatized to each run. So basically, I think those aren't actually mentioned in this particular snippet I pulled out, but further down the line is just they're kind of like temp variables holding information that you want to not necessarily have each parallel thread writing into and overwriting. The inner loop within this do loop is then now the final vector loop that is actually collapsed into doing this computation across all the vertical levels, plus the number of scalars within each cell that we're operating on. And so this is a typical kind of like arrangement of how you can make something run on GPU and add some additional specifications to make sure it does it correctly. Any questions for like this example and how this is done? So again, like the highlighting, just like the ease of access of this is we're simply adding comments here. This is still the original like CPU code that you could keep. If you don't have a GPU, you can still run as a CPU code. But we've only added, at least for this small section, we've only added like 3 lines here to specify to put it onto the GPU. Merely, we did not manage any of the data part of it yet, which it is managed earlier in the code, but nonetheless, it's not a lot of work here to enable this GPU version of this of the model, and thus hopefully you at least perceive this as much more accessible, say, compared to if we had to do this all in CUDA. It would be a lot more work to like suss through all the different details to get this running in CUDA and managing thread ID and block IDX and all those sort of more interesting ways you can optimize CUDA kernels and have to program that. So I value the OpenACC approach, even though you don't get as much finesse towards the granularity of control that CUDA provides. It's a much easier approach and saves my time towards focusing on different parts of the model, say, or squashing bugs as it might come up over time, compared to a more difficult process of doing CUDA, which just takes significantly more time for each kernel we have to rewrite. So, another thing to point out that's I find very important is that the compiler will often provide you a diagnostic section of what it's actually doing whenever you compile this code. For example, the minfo Excel flag is often very useful to include in the your compilation flag options. It's actually included by default in the make sequence that's included with MPAS 8.2, I believe. So this adds details to the compiler log and make output about what offloading configurations were chosen by the compiler. So from the previous example, this was started. This do line is at line 3246. It's basically saying, oh, we are doing that some additional private variables where we actually didn't need to specify, but it's specifying for you. But if it's doing something you don't want it to do, you can also see that like, hey, it's doing something. Should it be doing that? You can evaluate that and maybe change it as needed. But nonetheless, it actually confirms it's generating NVIDIA GPU code. If you're on an AMD system, it would say in generating an AMD GPU code. And it's, we got to like one of the loops here, there's the gain worker loop, and it's saying it decided to do a worker of size unit 4 for those gain and worker distributions. And when it gets to the vector loop that we specified, as well as the also collapse loop, which it's honoring because it's mentioning it here, it shows a vector size of 32. If you wanted to change any of those sizes, you could add those as arguments to your clauses, and you could see if that improves or decreases the performance of your model as you say try different vector or worker sizes. There's also a vector barrier inserted due to potential dependence out of a vector loop. So basically, that's just saying, there's some dependence that the compiler is seeing in terms of between some of the loops, and it's making sure that it's not getting ahead of itself in its instructions to say overwrite some of the data due to that dependence. But there can be a signifier of some excess weight going on, like wait time that's being added to the kernel runtime. And so if you see that type of warning, you might say look at different ways to design that kernel such that it doesn't have to insert those barriers. Overall, it's just important to review this information to ensure the compiler is doing actually what you wanted it to do. Sometimes it does things you didn't want it to do and be like, oh, wait, maybe I missed a comma somewhere or something. And this type of diagnostic report is helpful towards identifying those issues. Any questions here about compute constructs in OpenACC? Yeah.
Doesn't write the OpenACC code, but as a scientist who writes the Fortran code, and I recognize the code you have in there and where it's going, what's coming after it, for example, that might have generated some of the messages in that log file, like the vector barrier inserted because you've got other variables that you're computing further down in that cell loop over the columns.
Right.
Are there plans to add some more commentary in the actual code so that maybe those of us who aren't as familiar with this will have an understanding of here's where you need to be careful or something, because I don't understand most of what's coming up in that commentary there.
Right.
So, but I can see where it's important to see that, so you can see when it's being compiled what it's actually trying to do or what it thinks it's doing. I can see that. But are there plans to write more to comment the actual code before compiling, so that those of us whom are not experts in this will have a better sense of maybe what's being inserted is actually doing?
Well, I'm glad you bring that up, and at least I'll clarify first. Like, I'm not a primary developer of MPAS. I'm just support a lot of the GPU development efforts across NCAR in general. But nonetheless, I think that brings to the point earlier made in terms of like how you are engaging effectively the software engineers within your team and your work, and like if you want the expectation of like improving documentation commenting practices, like be a part of the meeting and like ask us like, hey, you made this change to the code. Like, I don't quite understand it. Can you like add a comment there? And even then like setting that standard expectation throughout the development process so that you as a user and, part-time developer of the code, maybe not wishing to be a full-time, OpenACC expert, but still wanting to know what's going on. If you're adding the expectation as part of your team expectations, I think that is very much a golden rule oftentimes in software engineering. I love it when I see documentation and comments because I can understand the code better, but there's too many times where I'm like triaging issues with people, whereas like there's no documentation, no comments at all, and I'm sad. So I think many software engineers would agree that like, getting your colleagues to standardize and expect commenting like that is for not only their own value, but also for your own. So this is part of the agreed values you need to like express with your team and colleagues. So the last section here, I focus more on the data construct sections. So previously we were focusing just on the compute constructs. And so anytime if we didn't have any data constructs at the time, but any compute construct will still have an implicit data region. So anytime the compiler encounters a region, it'll look inside the variables within that compute region, be like, oh, variable X is here, variable Y is here. I need to make sure that I move variable X and Y onto the GPU before I do that work. And it'll like apply some operation in the background to make sure that data movement can happen. So anytime you have a parallel region, there's then that implicit data region that happens that makes sure the CPU memory gets moved into the GPU memory before the parallel region actually works. Without data management, transfers will often become redundant. So if you just have like a parallel region with a implied data region around that, or even you specify one only around the data region, you'll say every time you count it, you're copying variables, or say if it's a copy operation, I'll copy in and copy out. But it's doing this 6 times or how many times that loop repeats, even though you may not need the data on the CPU in the space between these kernels, running. So, without data management, you can easily be doing some redundant movement that's not ideal. However, if you instead identify what data can stay on the GPU and what doesn't need to move back and forth every single iteration, you can then minimize that movement. So if you say encapsulate your full sequence of parallel compute regions, say like your full loop or time loop, for example, you can then say like, oh, this data, the column matrices or whatever it might be, that should be on the GPU the whole time, and I don't necessarily need the data back until I complete the full operation. So you can surround all those regions within a single compute region, and that's saying you're only copying it in once, or only copying it out once, or etc. Whatever need you might have the data, as opposed to doing that every single time within these compute regions. So by specifying data movement and understanding where you need data moved and not moved, that can minimize those amount of data movements and that excessive cost there, as I was highlighting earlier, just because of that bandwidth capacity between the CPU and GPU is very small. So anytime you have to move data, that's bad news. So thinking about how we're designing and putting data barriers between how it's being operated on, that's important to make sure we're achieving optimal performance as we might want. So there are 2 types of data regions. There's structured data regions and unstructured data regions. So compute constructs typically will have just within themselves a structured data region. They will have, as I said, that implicit one. There's also data construct regions you can specify yourself, say with ACC data and ACCN data, that will kind of encapsulate itself between those 2. And then there's some like implicit data regions through some special variables. I won't go into much through the ACC declare variable. Each of these structured regions use reference counters to keep track of whether or not a data movement has happened or not. And in the same sense, for a unstructured data region, they'll now use dynamic reference counters, but they're not tied to specific regions. You can say, I'm going to move data at this point with an enter data region, where it's like a copy or copy in type operation typically, or a exit data region where it's a copy out type operation. Nonetheless, like these and most modern codes, I imagine most people working with, the unstructured data regions will be preferred, because you often instantiate the data much further away from where the compute might be happening within the code itself. So you might say, after say allocating memory for data, you'll say, I'm going to move that to the data or create it, allocate it on the GPU. And that would be done in a enter data region here, or exit data region when you're say at the end of the runtime and you want to delete data from the GPU. There are different benefits and pros and cons to each, but understanding how that kind of works is helpful towards managing that. And I'm highlighting this reference counter kind of issue here as well, in the sense of there's all these implied data regions or other data regions that show up, and maybe you're only concerned of like that starting and that copy in, but you maybe as you're doing iterative development, you might say put a parallel region, but then you can encapsulate it with its own data region, and just to make sure you're understanding which data is needed where, because you have that information then in the code. But later on, you encapsulate it in a much larger data region. So that much larger data region, say, for example, you start moving in variable A, then you have an A_D on the a device variable version of variable A. When you move into this copy in place here, that reference counter increases by 1. There's still that copy in kind of like specification may be happening within this parallel region here. But since this reference counter is positive, it's not 0, it won't actually do any data movement. So it will only say do data movement once it's say, every time it enters a region, it increments it. When it exits a region, it decrements that counter. And when it gets say to the end and actually gets back to 0, that's when it does that final movement if it asks for it. So copy in only does movement at the beginning of the region. Copy does movement at the end, beginning and end, but it only do that operation, say, when that reference counter either starts from 0 or goes down to 0. So, you know, this is just helpful in the sense of like how you might do incremental development with OpenACC, where like you can not necessarily think about the larger where data exists around the whole code until the end of the model. And like you can say each individual GPU kernel can have its own like data management assigned to it. And at some point later on, you have like a larger region, and that larger region will still like manage those reference counters for you, such that you'll still avoid those excessive movements, even though you're specifying a potential copy that might happen somewhere. It will only do that copy if it needs to do that copy. And these reference counters will keep track of whether or not that need is required or not. So some examples here for a simple case. You know, we have a structured data region. Say we have some kernels we're running. You know, we can surround that kernel with just a, you know, a data, copy this variable 1 here. Maybe variable 1 is called within this kernel and this kernel here. And when we're ending that region and no longer care about the data as much, we can actually end the data here. So we use copy. This will copy in here and then copy out the end. If you had the copy in clause, it would only copy in and then not just leave it on the GPU once it exited. Or it might deallocate it if at the end, but it depends if you're like you know, terminating the runtime or not. Otherwise, there's also unstructured data directives. So say you know, anywhere earlier in the code, say you allocated a variable, then you can immediately copy in that variable, and it'll take place right when that happens. And then you can have an exit data as well anywhere as well. Typically, enter data is associated with copy in or create or copy, but like there won't be a copy out ever with a if you specify copy with an enter data directive. But a copy out does not apply for enter data. It's more of just a syntax helper thing there in terms of, you know, if you try to put copy out here, you'll show an error, be like, why are you trying to do that? And you'll hopefully fix it and see what needs to change. See, I think I have 5 minutes left, so I want to make sure how much time I have left. So in any case, another important point here are the update and present clauses. The update construct is actually a construct, it's not a clause. The update construct allows you to immediately move data onto the GPU or GPU and doesn't necessarily use a counter in those cases. Say like, you know, at some point, say like every 100 iterations, you want to move data off the GPU, you typically would use the update clause there to say, hey, it's reached the 100th iteration. I want the state of the model. I want the state of this data. I want to update it back to the host. And then once the host gets it, it can write it out to a file. That's typically the use case of that host of the update clause. But keep in mind, every time you use update, it is doing that data movement. It is, you are incurring that data movement cost. The next one is present. Basically, you can add the present clause and it'll say that data should already be present on the GPU. You do not need to move it. It'll still do a check just to make sure it's there, but nonetheless, it gives a hint to the compiler to like not add an implicit, say, copy that might say typically try to do if it can't find in the source code an original allocation of the data already. So those can be helpful. Also, just keeping your sanity and just knowing which data is already present within a compute kernel as you're writing out the code and reading it back to yourself, trying to understand what's happening. Another piece of the puzzle here that is important towards achieving significant performance with GPU code is asynchronous execution. So as you schedule kernels onto the GPU, they'll often run in queue to streams. If you do not specify the stream or any async type operation, it'll go into the default stream. That's like one stream will always run on, and it'll run sequentially within that one stream. So by default, everything is run in a synchronous execution. The host must wait, the CPU must wait for each parallel compute region to finish, or data region to finish before it will move on to the next one. And all operations and parallel tasks must run in a serialized cut sequence. However, with asynchronous execution, you can then, the CPU can proceed down past each kernel as it schedules it until it hits like a wait operation or something, and basically allow tasks to accumulate and queue up onto the GPU and run right after each other without having to wait for the CPU to schedule a new task. So that can help speed things up. You can also, through asynchronous type operations, manage multiple streams, and multiple streams can run concurrently with each other. So say you can have like stream 2, like managing data movement, but stream 1 is doing compute, and those can run at the same time. So you can allow data to get prepared for the next step in your like time step while the current time step is running, and that can help speed up performance the same. So like, pipelining is part of like that concept of what's happening. Typically by default, you might have a host to device data movement, then you run the kernel, then you want to move the data back to the host. And you might do that over and over again. But if you do this in a more asynchronous manner, and you're specifying the streams it might be running on, you can then say, start, having the kernel and host device movement, memory movement happen at the same time, and they can stack on each other, and they can, allow you to like save some time, use a physically shorter, kind of example here, amount of time spent for three kernel runs versus like, how much longer it would be for 3 kernel runs if they're all serialized into one stream. So asynchronicity is an important piece to think about there. So when you see that async clause there, if someone else has written that is what's happening as you're doing that. But it's important to think about what is appropriate in terms of which streams are being added where, such that data is not being overwritten or missed or preemptively operated on, etc. And so it takes some forethought in how to do that effectively. Those are done with the async and wait clauses. So if you add async to any construct, it'll schedule that kernel into the nth stream you can specify. And you can also use the wait one. I want to wait on a specific stream to finish before this kernel to run, or basically we'll block the host or CPU to wait until certain things will run moving forward. So those sort of like clauses help dictate that, and is especially helpful towards packing in as much more operations concurrently on the GPU at the same time. So with my last couple of minutes, I won't have time to go into profilers performance, but I just wanted to offer this slide here in terms of like, the Nsight Systems Profiler is one that's very valuable in terms of like assessing the actual runtime and what's happening within your code. And so it'll give you like a visual representation of, say, like, I call this semi-discrete time step here, and the next one is the time step 2 or 3 or whatever. And like in this section is like a data movement that's happening. You can see like the GPU is kind of just like idle while that data movement is happening. So maybe there's something compute-wise you could add there, but in that particular model, we probably did not have the opportunity. But you can visualize those sort of like the runtime of your model, such that if you see excessive like white space, or in this case, since it's dark mode, dark space, if you see excessive white space, that means that the GPU is idle, and you may have an opportunity to add more work to the GPU or reconfigure how your model is designed. So it's important just to consider this like process as like a part of your iterative development cycle. As you say, adding more features, it's useful to profile and reprofile just to see if you've actually achieved performance improvement, worsened it even, and say if performance decreased, be like, hey, what did I change? Should I do something differently? And like it can help you say, as you make more and more changes, say not have to like go back in time, be like, okay, which one caused my performance to degrade? And so it's better to catch issues earlier on than later. So doing this in such a way where like maybe you're profiling every single time you make a significant change, that's helpful towards squashing bugs before they happen, so to speak, or at least and not accumulating too many at the same time. So just as a last point here, the porting MPAS V8 to GPUs for OpenACC, the effort is ongoing and still a work in progress from how I understand it. Some of the work has already been done specifically within this source file here, which you can look into. You can Control F, for example, and find the ACC directives there to see what it's already doing. There were past efforts on the version 6 of the model. And there's, for example, there's a paper about the WSSM6 microphysics scheme and computers and geosciences about their implementation of that. And there's a documentation on V6. But from what I understand, the goal is to move on to new implementations and how it's changed to V8. So there remain significant opportunities to collaborate with current MPAS and future developers to refresh those GPU porting efforts for the version 8 version. So I would highly recommend you seek out those collaborations with RSCs and making sure you're engaging them in the process to identify the best practices and opportunities to make sure your model is functional on the hardware of the future, because more and more clusters and HPC centers are relying on GPUs, and CFD type models tend to be pretty favorable towards using GPUs effectively. So it would be a significant loss if you're not planning for that future of making sure your software runs on GPUs. So that's about all I have. There's some additional resources you're welcome to review. You know, this was some of these materials are actually part of a 16-part series of some various topics in GPU training and development. Some of it also included machine learning and such, which I didn't really talk on much here. But you're welcome to go to that GitHub page. It was using Manyweather as an example, predominantly for learning GPU computing. There's also some additional documents and a best practices guide and reference guide, standard specifications that you're welcome to reference for learning OpenACC better. And if you want to learn CUDA, or at least like would want to encourage one of your colleagues to, I often will recommend this CUDA training series, or Oak Ridge National Lab offered ways back if you need more higher improvement for NVIDIA specific GPU runtimes of specific kernels within your model. So that's all I have. If you have any questions, feel free to reach out to me via email, or if you are using our clusters here, you're more than welcome to reach out to our HPC user help desk at the rchelp.ucar.edu. One of myself or one of my teams will are typically happy and eager to triage and support any issues you might have, or at least connect you with other folks that might be more well equipped to deal with this, to deal with issues you might have with MPAS development and use. Nonetheless, I appreciate your time and having me, and happy to take any other questions.
So I went straight to CUDA and some of the satellite work I did, but apparently for some of the Hellcast stuff I still have to do, I should probably go back to OpenACC and make my life easier. But so from what it seemed from you, is probably the biggest problem is just moving data from CPU memory to GPU memory. So we've had, and I haven't attempted Metal, but Apple has that system on a chip where they share it now. And I realize why Intel and NVIDIA don't do that, because they're separate things. But I'm wondering if that's a huge problem. Why haven't we seen anything from like AMD with the whole system on a chip? They both share the same memory kind of thing. Because that seems like that would be a huge boon to us, at least.
Yeah, it's a great point to bring up, because and unfortunately, I'm not too familiar with like Metal's implementation with Apple's SoCs. But I believe even in all those contexts, it's still important to highlight the data movement, because there's still some distinguishing factor, even on the SoC type chips, of the memory that's for CPU side use and memory that's for GPU side use. But as a benefit that may alleviate this problem, at least to some significant extent, is that the newer Grace Hopper and Blackwell chips will have a much more unified memory space between the CPU and GPU. So there's for the Grace Hopper chips that have a CPU integrated within the NVIDIA GPU hardware, like die, supposedly that will offer that there'd be less of a concern of the data movement between the two types of memory. Nonetheless, I've been told that there's still some loss incurred if you do not manage that memory appropriately. So it's it's still important to not be too lazy of a programmer and figuring out how to like manage that memory better. So, but yes, there are lots of opportunities in those systems on a chip type of opportunities coming out.
Also, just to elaborate a little bit more on Apple Metal, at my previous company, which was a computational chemistry company, one of the molecular dynamic engines we used, OpenMM, actually, someone had a lot of time on their hands and they redid most of their GPU code in Apple Metal. And where you really saw a hit to performance was when in the areas where you would benefit from NVIDIA's tensor cores. So like being able to switch from like double to mixed precision stuff. The Metal chips are just like not really there yet. But I was actually just going over, I think it's a tutorial on NVIDIA's website by Mark Harris, who's one of their primary GPU developers. And it was on parallel reductions, which are very popular GPU operations used for sorting and summations and all that stuff, where to an untrained eye, the first iteration of the reduction algorithm looks really similar to the 7th iteration. But performance-wise, there's a 23% 23x increase in the last iteration. And it is just tweaking shared memory, unrolling loops when you can, doing very specific templated memory interweaving operations. Does OpenACC, is it, I guess, smart enough from what you've seen to like make these very subtle optimizations, or is it kind of like it will just get you like a decent implementation of a GPU kernel?
I would say in my experience, it's more often on the latter of like this. It'll get you decent implementation. Nonetheless, there are opportunities to play around with like there's like a advanced clause that you can use called the cache clause. Just as you specify, this variable needs to be in like the cache for these like games that you used to like making sure that that's like accessed in a faster way. Whether or not that can be accommodated for memory interweaving, for example, I do not know OpenACC to be friendly towards that, but if that is a specific functionality that you envision because I'm not thinking top of my head like how best effectively to do that within the directive context, but the OpenACC developer committees and such, Jeff Larkin I think is one that mainly leads that. They very much welcome folks to engage with them and be like, hey, like this feature would be really cool if there's a way we could do this. And I'm part of the OpenACC leadership board in terms of managing some of the discussions amongst the community. So I could be happy to connect you with Jeff and other folks if that's of interest.
Cool, thanks.
Other questions? I wanted to keep you too much from actual lunch. I guess that's also the last session, so. Yeah. Well, thanks everyone, and I hope everyone appreciated your MPAS WRF workshop this year. I don't know if you have any other announcements to add or anything. Nope. Oh, maybe.
No, I think we're fine, we're just finished at this point. Yeah, thank you for coming and talk to us about GPU. Yeah, sure. Yeah. Any other questions? I don't have, there are any questions from the online participant. So anything else from here? Yeah. Hey, yeah, thank you. Thank everybody else for participating. Yeah, and we'll hope to see you again maybe next year. Okay. Bye.